Chapter 2. The performance of an aircraft is the most important feature which defines its suitability for specific missions. The principal items of airplane performance deserve detailed consideration in order to better understand and appreciate the capabilities of each airplane. Knowledge of the various items of airplane performance will provide the naval aviator with a more complete appreciation of the operating limitations and insight to obtain the design performance of his aircraft. The performance section of the Flight Handbook provides the specific information regarding the capabilities and limitations of each airplane. Every naval aviator must rely upon these handbook data as the guide to safe and effective operation of his aircraft. Required thrust and power. Definitions. All of the principal items of flight performance involve steady-state flight conditions and equilibrium of the airplane. For the airplane to remain in steady level flight, equilibrium must be obtained by a lift equal to the airplane weight and a power plant thrust equal to the airplane drag. Thus, the airplane drag defines the thrust required to maintain steady level flight. The total drag of the airplane is the sum of the parasite and induced drags. Parasite drag is the sum of pressure and friction drag which is due to the basic configuration and, as defined, is independent of lift. Induced drag is the undesirable but unavoidable consequence of the development of lift. In the process of creating lift by the deflection of an airstream, the actual lift is inclined, and a component of lift is incurred parallel to the flight path direction. This component of lift combines with any change in pressure and friction drag due to change in lift to form the induced drag. While the parasite drag predominates at high speed, induced drag predominates at low speed. Figure 2.1 illustrates the variation with speed of the induced, parasite, and total drag for a specific airplane configuration in steady level flight. The power required for flight depends on the thrust required and the flight velocity. By definition, the propulsive horsepower required is related to thrust required and flight velocity by the following equation. PR equals TR times V over 325. Where PR equals power required in horsepower, TR equals thrust required or total drag in pounds, and V equals true airspeed in knots. By inspection of this relationship, it is apparent that each pound of drag incurred at 325 knots requires 1 horsepower of propulsive power. However, each pound of drag at 650 knots requires 2 horsepower while each pound of drag at 162.5 knots requires 1/2 horsepower. The term power implies work rate and, as such, will be a function of the speed at which a particular force is developed. Distinction between thrust required and power required is necessary for several reasons. For the items of performance such as range and endurance, it is necessary to relate powerplant fuel flow with the propulsive requirement for steady level flight. Some power plants incur fuel flow rate according to output thrust while other power plants incur fuel flow rate depending on output power. For example, the turbojet engine is principally a thrust-producing machine, and fuel flow is most directly related to thrust output. The reciprocating engine is principally a power-producing machine, and fuel flow is most directly related to power output. For these reasons, the variation of thrust required will be of greatest interest in the performance of the turbojet-powered airplane while the variation of power required will be of greatest interest in the performance of the propeller-powered airplane. Also, distinction between power and thrust required is necessary in the study of climb performance. During a steady climb, the rate of climb will depend on excess power while the angle of climb is a function of excess thrust. The total power required for flight can be considered as the sum of induced and parasite effects similar to the total drag of the airplane. The induced power required is a function of the induced drag and velocity. PR sub I equals capital D sub I times V over 325. Where PR sub I equals induced power required in horsepower, capital D sub I equals induced drag in pounds, and V equals true airspeed in knots. Thus, induced power required will vary with lift, aspect ratio, altitude, etc., in the same manner as the induced drag. The only difference will be the variation with speed. If all other factors remain constant, the induced power required varies inversely with velocity while induced drag varies inversely with the square of the velocity. PR sub I2 over PR sub I1 equals V sub 1 over V sub 2. Where PR sub I1 equals induced power required corresponding to some original speed, V sub 1, and PR sub I2 equals induced power required corresponding to some different speed, V sub 2. For example, if an airplane in steady level flight is operated at twice as great a speed, the induced drag is 1/4 the original value, but the induced power required is 1/2 the original value. The parasite power required is a function of the parasite drag and velocity. PR sub P equals capital D sub P times V over 325. Where PR sub P equals parasite power required in horsepower, capital D sub P equals parasite drag in pounds, and V equals true airspeed in knots. Thus, parasite power required will vary with altitude and equivalent parasite area, lowercase f, in the same manner as the parasite drag. However, the variation with speed will be different. If all other factors are constant, the parasite drag varies as the square of velocity, but parasite power varies as the cube of velocity. PR sub P2 over PR sub P1 equals the quantity V sub 2 over V sub 1 squared. Where PR sub P1 equals parasite power required corresponding to some original speed, V sub 1, and PR sub P2 equals parasite power required corresponding to some different speed, V sub 2. For example, if an airplane in steady flight is operated at twice as great a speed, the parasite drag is 4 times as great, but the parasite power required is 8 times the original value. Figure 2.1 presents the thrust required and power required for a specific airplane configuration and altitude. The curves of Figure 2.1 are applicable for the following airplane data. Gross weight, capital W, equals 15,000 pounds. Span, lowercase b, equals 40 feet. Equivalent parasite area, lowercase f, equals 7.2 square feet. Airplane efficiency factor, lowercase e, equals 0.827. Sea level altitude, lowercase sigma, equals 1.000. Compressibility corrections neglected. The curve of drag or thrust required versus velocity shows the variation of induced, parasite, and total drag. Induced drag predominates at low speeds. When the airplane is operated at maximum lift-to-drag ratio, L over D max, the total drag is at a minimum, and the induced and parasite drags are equal. For the specific airplane of Figure 2.1, L over D max and minimum total drag are obtained at a speed of 160 knots. The curve of power required versus velocity shows the variation of induced, parasite, and total power required. As before, induced power required predominates at low speeds, and parasite power required predominates at high speeds, and the induced and parasite power are equal at L over D max. However, the condition of L over D max defines only the point of minimum drag and does not define the point of minimum power required. Ordinarily, the point of minimum power required will occur at a speed which is 76% of the speed for minimum drag and, in the case of the airplane configuration of Figure 2.1, the speed for minimum power required would be 122 knots. The total drag at the speed for minimum power required is 15% higher than the drag at L over D max, but the minimum power required is 12% lower than the power required at L over D max. Induced drag predominates at speeds below the point of minimum total drag. When the airplane is operated at the condition of minimum power required, the total drag is 75% induced drag and 25% parasite drag. Thus, the induced drag is 3 times as great as the parasite drag when at minimum power required. Variations of thrust required and power required. The curves of thrust required and power required versus velocity provide the basis for comprehensive analysis of all the major items of airplane performance. The changes in the drag and power curves with variations of airplane gross weight, configuration, and altitude furnish insight for the variation of range, endurance, climb performance, etc., with these same items. The effect of a change in weight on the thrust and power required is illustrated by Figure 2.2. The primary effect of a weight change is a change in the induced drag and induced power required at any given speed. Thus, the greatest changes in the curves of thrust and power required will take place in the range of low-speed flight where the induced effects predominate. The changes in thrust and power required in the range of high-speed flight are relatively slight because parasite effects predominate at high speed. The induced effects at high speed are relatively small, and changes in these items produce a small effect on the total thrust or power required. In addition to the general effect on the induced drag and power required at particular speeds, a change in weight will require that the airplane operate at different airspeeds to maintain conditions of a specific lift coefficient and angle of attack. If the airplane is in steady flight at a particular CL, the airspeed required for this CL will vary with weight in the following manner. V sub 2 over V sub 1 equals the square root of W sub 2 over W sub 1. Where V sub 1 equals speed corresponding to a specific CL and weight, W sub 1, and V sub 2 equals speed corresponding to the same CL but a different weight, W sub 2. For the example airplane of figure 2.2, a change of gross weight from 15,000 to 22,500 pounds requires that the airplane operate at speeds which are 22.5% greater to maintain a specific lift coefficient. For example, if the 15,000-pound airplane operates at 160 knots for L over D max, the speed for L over D max at 22,500 pounds is V sub 2 equals V sub 1 times the square root of W sub 2 over W sub 1. Or, V sub 2 equals 160 times the square root of 22,500 over 15,000. Or, V sub 2 equals 160 times 1.1225. Or, V sub 2 equals 196 knots. The same situation exists with respect to the curves of power required, where a change in weight requires a change of speed to maintain flight at a particular CL. For example, if the 15,000-pound airplane achieves minimum power required at 122 knots, an increase in weight to 22,500 pounds increases the speed for minimum power required to 149 knots. Of course, the thrust and power required at specific lift coefficients are altered by changes in weight. At a specific CL, any change in weight causes a like change in thrust required, e.g., a 50% increase in weight causes a 50% increase in thrust required at the same CL. The effect of a weight change on the power required at a specific CL is a bit more complex, because a change in speed accompanies the change in drag, and there is a twofold effect. A 50% increase in weight produces an increase of 83.8% in the power required to maintain a specific CL. This is the result of a 50% increase in thrust required coupled with a 22.5% increase in speed. The effect of a weight change on thrust required, power required, and airspeed at specific angles of attack and lift coefficients provides an important basis for various techniques of cruise and endurance conditions of flight. Figure 2.3 illustrates the effect on the curves of thrust and power required of a change in the equivalent parasite area, f, of the configuration. Since parasite drag predominates in the region of high flight speed, a change in f will produce the greatest change in thrust and power required at high speed. Since parasite drag is relatively small in the region of low speed flight, a change in f will produce relatively small changes in thrust and power required at low speeds. The principal effect of a change in equivalent parasite area of the configuration is to change the parasite drag at any given airspeed. The curves of figure 2.3 depict the changes in the curves of thrust and power required due to a 50% increase in equivalent parasite area of the configuration. The minimum total drag is increased by an increase in f, and the L over D max is reduced. Also, the increase in f will increase the CL for L over D max and require a reduction in speed at the new, but decreased, L over D max. The point of minimum power required occurs at a lower airspeed, and the value of the minimum power required is increased slightly. Generally, the effect on the minimum power required is slight because the parasite drag is only 25% of the total at this specific condition of flight. An increase in the equivalent parasite area of an airplane may be brought about by the deflection of flaps, extension of landing gear, extension of speed brakes, addition of external stores, etc. In such instances, a decrease in the airplane efficiency factor, e, may accompany an increase in f to account for the additional changes in parasite drag which may vary with CL. A change in altitude can produce significant changes in the curves of thrust and power required. The effects of altitude on these curves provide a great part of the explanation of the effect of altitude on range and endurance. Figure 2.4 illustrates the effect of a change in altitude on the curves of thrust and power required for a specific airplane configuration and gross weight. As long as compressibility effects are negligible, the principal effect of increased altitude on the curve of thrust required is that specific aerodynamic conditions occur at higher true air speeds. For example, the subject airplane at sea level has a minimum drag of 1,250 pounds at 160 knots. The same airplane would incur the same drag at altitude if operated at the same equivalent airspeed of 160 knots. However, the equivalent airspeed of 160 knots at 22,000 feet altitude would produce a true airspeed of 227 knots. Thus, an increase in altitude will cause the curve of thrust required to flatten out and move to the direction of higher velocity. Note that altitude alone will not alter the value of minimum drag. The effect of altitude on the curve of power required can best be considered from the effect on true airspeed to achieve a specific aerodynamic condition. The sea level power required curve of figure 2.4 indicates that L/D max occurs at 160 knots and requires 615 horsepower. If this same airplane is operated at L/D max at an altitude of 22,000 feet, the same drag is incurred at a higher velocity and requires a higher power. The increase in velocity to 227 knots accounts for the increase in power required to 872 horsepower. Actually, the various points on the curve of power required can be considered affected in this same fashion. At specific lift coefficients and angles of attack, a change in altitude will alter the true airspeed particular to these points and cause a change in power required because of the change in true airspeed. An increase in altitude will cause the power required curve to flatten out and move to higher velocities and powers required. The curves of thrust and power required and their variation with weight, altitude, and configuration are the basis of all phases of airplane performance. These curves define the requirement of the airplane and must be considered with the power and thrust available from the power plants to provide detailed study of the various items of airplane performance. Available thrust and power. Principles of propulsion. All power plants have in common certain general principles. Regardless of the type of propulsion device, the development of thrust is related by Newton's laws of motion. F equals ma, or F equals d/dt times mv, where F equals force or thrust in pounds, m equals mass in slugs, a equals acceleration in feet per second squared, d/dt equals derivative with respect to time, e.g., rate of change with time, and m times v equals momentum in pound seconds, the product of mass and velocity. The force of thrust results from the acceleration provided to the mass of working fluid. The magnitude of thrust is accounted for by the rate of change of momentum produced by the power plant. A rocket power plant creates thrust by creating a very large change in velocity of a relatively small mass of propellants. A propeller produces thrust by creating a comparatively small change in velocity of a relatively large mass of air. The development of thrust by a turbojet or ramjet power plant is illustrated by figure 2.5. Air approaches at a velocity, v/1, depending on the flight speed, and the power plant operates on a certain mass flow of air, capital Q, which passes through the engine. Within the power plant, the air is compressed, energy is added by the burning of fuel, and the mass flow is expelled from the nozzle, finally reaching a velocity, v/2. The momentum change accomplished by this action produces the thrust. Ta equals capital Q times the quantity v/2 minus v/1. Where Ta equals thrust in pounds, capital Q equals mass flow in slugs per second, v/1 equals inlet or flight velocity in feet per second, and v/2 equals jet velocity in feet per second squared. The typical ramjet or turbojet power plant derives its thrust by working with a mass flow relatively smaller than that of a propeller, but a relatively greater change of velocity. From the previous equation, it should be appreciated that the jet thrust varies directly with the mass flow, capital Q, and velocity change, v/2 minus v/1. This fact is useful in accounting for many of the performance characteristics of the jet power plant. In the process of creating thrust by momentum change of the airstream, a relative velocity, v/2 minus v/1, is imparted to the airstream. Thus, some of the available energy is essentially wasted by this addition of kinetic energy to the airstream. The change of kinetic energy per time can account for the power wasted in the airstream. Pw equals Ke/T, or Pw equals capital Q over 2 times the quantity V sub 2 over V sub 1 squared. Of course, the development of thrust with some finite mass flow will require some finite velocity change, and there will be the inevitable waste of power in the airstream. In order to achieve high efficiency of propulsion, the thrust should be developed with a minimum of wasted power. The propulsion efficiency of the jet power plant can be evaluated by comparing the propulsive output power with the input power. Since the input power is the sum of the output power and wasted power, an expression for propulsion efficiency can be derived. Lowercase eta sub p equals PA over PA plus PW, or lowercase eta sub p equals 2 times V sub 1 over V sub 2 plus V sub 1. Where lowercase eta sub p equals propulsion efficiency, PA equals propulsive power available, or PA equals TA times V sub 1, and PW equals power wasted. The resulting expression for propulsion efficiency, lowercase eta sub p, shows a dependency on the flight velocity, V sub 1, and the jet velocity, V sub 2. When the flight velocity is 0, the propulsion efficiency is 0, since all power generated is wasted in the slipstream, and the propulsive power is 0. The propulsion efficiency would be 1.00, or 100%, only when the flight velocity, V sub 1, equals the jet velocity, V sub 2. Actually, it would not be possible to produce thrust under such conditions with a finite mass flow. While 100% efficiency of propulsion cannot be attained practically, some insight is furnished to the means of creating high values of propulsion efficiency. To obtain high propulsion efficiency, it is necessary to produce the required thrust with the highest possible mass flow and lowest possible velocity change. The graph of figure 2.5 shows the variation of propulsion efficiency, lowercase eta sub p, with the ratio of flight speed to jet velocity, V sub 1 over V sub 2. To achieve a propulsion efficiency of 0.85 requires that the flight velocity be approximately 75% of the slipstream speed relative to the airplane. Such a propulsive efficiency could be typical of a propeller-powered airplane which derives its thrust by the propeller handling a large mass flow of air. The typical turbojet power plant cannot achieve such high propulsive efficiency because the thrust is derived with a relatively smaller mass flow and larger velocity change. For example, if the jet velocity is 1,200 feet per second at a flight velocity of 600 feet per second, the propulsion efficiency is 0.67. The ducted fan, bypass jet, and turboprop are variations which improve the propulsive efficiency of a type of power plant which has very high power capability. When the conditions of range, endurance, or economy of operation are predominant, high propulsion efficiency is necessary. Thus, the propeller-powered airplane with its inherent high propulsive efficiency will always find application. The requirements of very high speed and high altitude demand very high propulsive power from relatively small power plants. When there are practical limits to the increase of mass flow, high output is obtained by large velocity changes and low propulsive efficiency is an inevitable consequence. Turbojet engines. The turbojet engine has found widespread use in aircraft propulsion because of the relatively high power output per power plant weight and size. Very few aircraft power plants can compare with the high output, flexibility, simplicity, and small size of the aircraft gas turbine. The coupling of the propeller and reciprocating engine is one of the most efficient means known for converting fuel energy into propulsive energy. However, the intermittent action of the reciprocating engine places practical limits to the airflow that can be processed, and restricts the development of power. The continuous, steady flow feature of the gas turbine allows such a power plant to process considerably greater airflow, and thus, utilize a greater expenditure of fuel energy. While the propulsive efficiency of the turbojet engine is considerably below that of the reciprocating engine-propeller combination, the specific power output of the turbojet at high speeds is quite superior. The operation of the turbojet engine involves a relatively large change in velocity being imparted to the mass flow through the engine. Figure 2.6 illustrates the operation of a typical turbojet engine by considering the processing given a unit weight of inlet airflow. Consider a unit weight of ambient air approaching the inlet to the engine then experiencing the changes in pressure and volume as it is processed by the turbojet. The chart of pressure versus volume of figure 2.6 shows that the unit weight of airflow at atmospheric condition A is delivered to the inlet entrance at condition B. The purpose of the inlet or diffuser is to reduce the velocity and increase the pressure of the flow entering the compressor section. Thus, the aerodynamic compression produces an increase in pressure and decrease in volume of the unit weight of air and delivers air to the compressor at condition C. The work done by the aerodynamic compression of the inlet or diffuser is represented by the area ABCX. Generally, most conventional turbojet engines require that the compressor inlet flow be subsonic, and supersonic flight will involve considerable aerodynamic compression in the inlet. Air delivered to the compressor inlet at condition C is then subject to further compression through the compressor section. As a result of the function of the compressor, the unit weight of air is subject to a decrease in volume and increase in pressure to condition D. The compressor pressure ratio should be high to produce a high thermal efficiency in the engine. The area XCDZ represents the work done by the compressor during the compression of the unit weight of air. Of course, certain losses and inefficiencies are incurred during the compression, and the power required to operate the compressor will be greater than that indicated by the work done on the engine airflow. Compressed air is discharged from the compressor to the combustion chamber at condition D. Fuel is added in the combustion chamber, and the combustion of fuel liberates considerable heat energy. The combustion process in the gas turbine differs from that of the reciprocating engine in that the process is essentially a constant pressure addition of heat energy. As a result, the combustion of fuel causes a large change in temperature and large change of volume of the unit weight of airflow. The process in the combustion chamber is represented by the change from point D to point E of the pressure volume diagram of figure 2.6. The combustion products are delivered to the turbine section, where sufficient work must be extracted to power the compressor section. The combustion chamber discharges high temperature, high pressure gas to the turbine, where a partial expansion is accomplished with a drop in pressure and increase in volume to point F on the pressure volume diagram. The work extracted from the unit weight of air by the turbine section is represented by the area ZEFY. As with the compressor, the actual shaft work extracted by the turbine will differ from that indicated by the pressure volume diagram because of certain losses incurred through the turbine section. For steady, stabilized operation of the turbojet engine, the power extracted by the turbine will equal the power required to operate the compressor. If the turbine power exceeds the compressor power required, the engine will accelerate. If the turbine power is less than the compressor power required, the engine will decelerate. The partial expansion of the gases through the turbine will provide the power to operate the engine. As the gases are discharged from the turbine at point F, expansion will continue through the tailpipe nozzle until atmospheric pressure is achieved in the exhaust. Thus, continued expansion in the jet nozzle will reduce the pressure and increase the volume of the unit weight of air to point G on the pressure volume diagram. As a result, the final jet velocity is greater than the inlet velocity, and the momentum change necessary for the development of thrust has been created. The area YFGA represents the work remaining to provide the expansion to jet velocity after the turbine has extracted the work required to operate the compressor. Of course, the combustion chamber discharge could be more completely expanded through a larger turbine section, and the net power could be used to operate a propeller rather than provide high exhaust gas velocity. For certain applications, the gas turbine-propeller combination could utilize the high power capability of the gas turbine with greater propulsive efficiency. Function of the components. Each of the engine components previously described will contribute some function affecting the efficiency and output of the turbojet engine. For this reason, each of these components should be analyzed to determine the requirements for satisfactory operating characteristics. The inlet or diffuser must be matched to the power plant to provide the compressor entry with the required airflow. Generally, the compressor inlet must receive the required airflow at subsonic velocity with uniform distribution of velocity and direction at the compressor face. The diffuser must capture high-energy air and deliver it at low Mach number uniformly to the compressor. When the inlet is along the sides of the fuselage, the edges of the inlet must be located such that the inlet receives only high-energy air, and provision must be made to dispose of the boundary layer along the fuselage surface. At supersonic flight speeds, the diffuser must slow the air to subsonic with the least waste of energy in the inlet air, and accomplish the process with a minimum of aerodynamic drag. In addition, the inlet must be efficient and stable in operation throughout the range of angles of attack and Mach numbers of which the airplane is capable. The operation of the compressor can be affected greatly by the uniformity of flow at the compressor face. When large variations in flow velocity and direction exist at the face of the axial compressor, the efficiency and stall surge limits are lowered. Thus, the flight conditions which involve high angle of attack and high side slip can cause deterioration of inlet performance. The compressor section is one of the most important components of the turbojet engine. The compressor must furnish the combustion chamber with large quantities of high-pressure air in a most efficient manner. Since the compressor of a jet engine has no direct cooling, the compression process takes place with a minimum of heat loss of the compressed air. Any friction loss or inefficiency of the compression process is manifested as an undesirable additional increase in the temperature of the compressor discharge air. Hence, compressor efficiency will determine the compressor power necessary to create the pressure rise of a given airflow and will affect the temperature change which can take place in the combustion chamber. The compressor section of a jet engine may be an axial flow or centrifugal flow compressor. The centrifugal flow compressor has great utility, simplicity, and flexibility of operation. The operation of the centrifugal compressor requires relatively low inlet velocities, and a plenum chamber or expansion space must be provided for the inlet. The impeller rotating at high speed receives the inlet air and provides high acceleration by virtue of centrifugal force. As a result, the air leaves the impeller at very high velocity and high kinetic energy. A pressure rise is produced by subsequent expansion in the diffuser manifold by converting the kinetic energy into static pressure energy. The manifold then distributes the high-pressure discharge to the combustion chambers. A double-entry impeller allows a given diameter compressor to process a greater airflow. The major components of the centrifugal compressor are illustrated in Figure 2.7. The centrifugal compressor can provide a relatively high pressure ratio per stage, but the provision of more than one or two stages is rarely feasible for aircraft turbine engines. The single-stage centrifugal compressor is capable of producing pressure ratios of about 3 or 4 with reasonable efficiency. Pressure ratios greater than 4 require such high impeller tip speed that compressor efficiency decreases very rapidly. Since high pressure ratios are necessary to achieve low fuel consumption, the centrifugal compressor finds greatest application in smaller engines where simplicity and flexibility of operation are the principal requirements rather than high efficiency. The axial flow compressor consists of alternate rows of rotating and stationary airfoils. The major components of the axial flow compressor are illustrated in Figure 2.7. A pressure rise occurs through the row of rotating blades, since the airfoils cause a decrease in velocity relative to the blades. An additional pressure rise takes place through the row of stationary blades, since these airfoils cause a decrease in the absolute velocity of flow. The decrease in velocity, relative or absolute, affects a compression of the flow and causes the increase in static pressure. While the pressure rise per stage of the axial compressor is relatively low, the efficiency is very high, and high pressure ratios can be obtained efficiently by successive axial stages. Of course, the efficient pressure rise in each stage is limited by excessive gas velocities. The multistage axial flow compressor is capable of providing pressure ratios from 5 to 10, or greater, with efficiencies which cannot be approached with a multistage centrifugal compressor. The axial flow compressor can provide efficiently the high pressure ratios necessary for low fuel consumption. Also, the axial compressor is capable of providing high airflow with a minimum of compressor diameter. When compared with the centrifugal compressor, the design and construction of the axial compressor is relatively complex and costly, and the high efficiency is sustained over a much narrower range of operating conditions. For these reasons, the axial compressor finds greatest application where the demands of efficiency and output predominate over considerations of cost, simplicity, flexibility of operation, etc. Multispool compressors and variable stator blades serve to improve the operating characteristics of the axial compressor and increase the flexibility of operation. The combustion chamber must convert the fuel chemical energy into heat energy and cause a large increase in the total energy of the engine airflow. The combustion chamber will operate with one principal limitation. The discharge from the combustion chamber must be at temperatures which can be tolerated by the turbine section. The combustion of liquid hydrocarbon fuels can produce gas temperatures which are in excess of 1,700 to 1,800 degrees Celsius. However, the maximum continuous turbine blade operating temperatures rarely exceed 800 degrees to 1,000 degrees Celsius, and considerable excess air must be used in the combustion chamber to prevent exceeding these temperature limits. While the combustion chamber design may take various forms and configurations, the main features of a typical combustion chamber are illustrated by Figure 2.8. The combustion chamber receives the high-pressure discharge from the compressor and introduces approximately one-half of this air into the immediate area of the fuel spray. This primary combustion air must be introduced with relatively high turbulence and quite low velocities to maintain a nucleus of combustion in the combustion chamber. In the normal combustion process, the speed of flame propagation is quite low and, if the local velocities are too high at the forward end of the combustion chamber, poor combustion will result, and it is likely that the flame will blow out. The secondary air, or cooling flow, is introduced downstream from the combustion nucleus to dilute the combustion products and lower the discharge gas temperature. The fuel nozzle must provide a finely atomized, evenly distributed spray of fuel through a wide range of flow rates. Very specialized design is necessary to provide a nozzle with suitable characteristics. The spray pattern and circulation in the combustion chamber must make efficient use of the fuel by complete combustion. The temperatures in the combustion nucleus can exceed 1700 to 1800 degrees Celsius, but the secondary air will dilute the gas and reduce the temperature to some value which can be tolerated in the turbine section. A pressure drop will occur through the combustion chamber to accelerate the combustion gas rearward. In addition, turbulence and fluid friction will cause a pressure drop, but this loss must be held to the minimum incurred by providing complete combustion. Heat transferred through the walls of the combustion chamber constitutes a loss of thermal energy and should be held to a minimum. Thus, the combustion chamber should enclose the combustion space with a minimum of surface area to minimize heat and friction losses. Hence, the annular-type combustion chamber offers certain advantages over the multiple-can-type combustion chamber. The turbine section is the most critical element of the turbojet engine. The function of the turbine is to extract energy from the combustion gases and furnish power to drive the compressor and accessories. In the case of the turboprop engine, the turbine section must extract a very large portion of the exhaust gas energy to drive the propeller in addition to the compressor and accessories. The combustion chamber delivers high-energy combustion gases to the turbine section at high pressure and tolerable temperature. The turbine nozzle vanes are a row of stationary blades immediately ahead of the rotating turbine. These blades form the nozzles which discharge the combustion gases as high-velocity jets onto the rotating turbine. In this manner, the high-pressure energy of the combustion gases is converted into kinetic energy, and a pressure and temperature drop takes place. The function of the turbine blades operating in these jets is to develop a tangential force along the turbine wheel, thus extracting mechanical energy from the combustion gases. This is illustrated in Figure 2.8. The form of the turbine blades may be a combination of two distinct types. The impulse-type turbine relies upon the nozzle vanes to accomplish the conversion of combustion gas static pressure to high-velocity jets. The impulse turbine blades are shaped to produce a large deflection of the gas and develop the tangential force by the flow direction change. In such a design, negligible velocity and pressure drop occurs with the flow across the turbine rotor blades. The reaction-type turbine differs in that large velocity and pressure changes occur across the turbine rotor blades. In the reaction turbine, the stationary nozzle vanes serve only to guide the combustion gas onto the turbine rotor with negligible changes in velocity and pressure. The reaction turbine rotor blades are shaped to provide a pressure drop and velocity increase across the blades, and the reaction from this velocity increase provides the tangential force on the wheel. Generally, the turbine design is a form utilizing some feature of each of the two types. The turbine blade is subjected to high centrifugal stresses which vary as the square of the rotative speed. In addition, the blade is subjected to the bending and torsion of the tangential impulse reaction forces. The blade must withstand these stresses which are generally of a vibratory and cyclic nature while at high temperatures. The elevated temperatures at which the turbine must function produce extreme conditions for structural creep and fatigue considerations. Consequently, the engine speed and temperature operating limits demand very careful consideration. Excessive engine temperatures or speeds may produce damage which is immediately apparent. However, creep and fatigue damage are cumulative, and even though damage may not be immediately apparent by visual inspection, proper inspection methods, other than visual, must be utilized, and proper records kept regarding the occurrence. Actually, the development of high-temperature alloys for turbines is a critical factor in the development of high-efficiency, high-output aircraft gas turbines. The higher the temperature of gases entering the turbine, the higher can be the temperature and pressure of the gases at discharge from the turbine with greater exhaust jet velocity and thrust. The function of the tailpipe or exhaust nozzle is to discharge the exhaust gases to the atmosphere at the highest possible velocity to produce the greatest momentum change and thrust. If a majority of the expansion occurs through the turbine section, there remains only to conduct the exhaust gases rearward with a minimum energy loss. However, if the turbine operates against a noticeable back pressure, the nozzle must convert the remaining pressure energy into exhaust gas velocity. Under ideal conditions, the nozzle would expand the flow to the ambient static pressure at the exhaust, and the area distribution in the nozzle must provide these conditions. When the ratio of exhaust gas pressure to ambient pressure is relatively low and incapable of producing sonic flow, a converging nozzle provides the expansion. The exit area must be of proper size to bring about proper exit conditions. If the exit area is too large, incomplete expansion will take place. If the exit area is too small, an overexpansion tendency results. The exit area can affect the upstream conditions and must be properly proportioned for overall performance. When the ratio of exhaust gas pressure to ambient pressure is greater than some critical value, sonic flow can exist, and the nozzle will be choked, or limited to some maximum flow. When supersonic exhaust gas velocities are required to produce the necessary momentum change, the expansion process will require the convergent-divergent nozzle illustrated in Figure 2.9. With sufficient pressure available, the initial expansion in the converging portion is subsonic, increasing to sonic velocity at the throat. Subsequent expansion in the divergent portion of the nozzle is supersonic, and the result is the highest exit velocity for a given pressure ratio and mass flow. When the pressure ratio is very high, the final exit diameter required to expand to ambient pressure may be very large, but is practically limited to the fuselage or nacelle afterbody diameter. If the exhaust gases exceed sonic velocity, as is possible in a ramjet combustion chamber or afterburner section, only the divergent portion of the nozzle may be necessary. Figure 2.9 provides illustration of the function of the various engine components, and the changes in static pressure, temperature, and velocity through the engine. The conditions at the inlet provide the initial properties of the engine airflow. The compressor section furnishes the compression pressure rise with a certain unavoidable, but undesirable increase in temperature. High-pressure air delivered to the combustion chamber receives heat from the combustion of fuel and experiences a rise in temperature. The fuel flow is limited, so that the turbine inlet temperature is within limits which can be tolerated by the turbine structure. The combustion takes place at relatively constant pressure and initially low velocity. Heat addition then causes large increases in gas volume and flow velocity. Generally, the overall fuel-air ratio of the turbojet is quite low because of the limiting turbine inlet temperature. The overall air-fuel ratio is usually some value between 80 to 40 during ordinary operating conditions because of the large amount of secondary air or cooling flow. High temperature, high-energy combustion gas is delivered to the turbine section where power is extracted to operate the compressor section. Partial or near-complete expansion can take place through the turbine section with the accompanying pressure and temperature drop. The exhaust nozzle completes the expansion by producing the final jet velocity and momentum change necessary in the development of thrust. Turbojet operating characteristics. The turbojet engine has many operating characteristics which are of great importance to the various items of jet airplane performance. Certain of these operating characteristics will provide a strong influence on the range, endurance, etc., of the jet-powered airplane. Other operating characteristics will require operating techniques which differ greatly from more conventional power plants. The turbojet engine is essentially a thrust-producing power plant, and the propulsive power produced is a result of the flight speed. The variation of available thrust with speed is relatively small, and the engine output is very nearly constant with flight speed. The momentum change, given the engine airflow, develops thrust by the following relationship. TA equals capital Q times the quantity V sub 2 minus V sub 1. Where TA equals thrust available in pounds, capital Q equals mass flow in slugs per second, V sub 1 equals inlet or flight velocity in feet per second, and V sub 2 equals jet velocity in feet per second. Since an increase in flight speed will increase the magnitude of V sub 1, a constant thrust will be obtained only if there is an increase in mass flow, capital Q, or jet velocity, V sub 2. When at low velocity, an increase in velocity will reduce the velocity change through the engine without a corresponding increase in mass flow, and the available thrust will decrease. At higher velocity, the beneficial ram helps to overcome this effect, and the available thrust no longer decreases, but increases with speed. The propulsive power available from the turbojet engine is the product of available thrust and velocity. The propulsive horsepower available from the turbojet engine is related by the following expression. PA equals TA times V over 325. Where PA equals propulsive power available in horsepower, TA equals thrust available in pounds, and V equals flight velocity in knots. The factor of 325 evolves from the use of the nautical unit of velocity, and implies that each pound of thrust developed at 325 knots is the equivalent of 1 horsepower of propulsive power. Since the thrust of the turbojet engine is essentially constant with speed, the power available increases almost linearly with speed. In this sense, a turbojet with 5,000 pounds of thrust available could produce a propulsive power of 5,000 horsepower at 325 knots or 10,000 horsepower at 650 knots. The tremendous propulsive power at high velocities is one of the principal features of the turbojet engine. When the engine RPM and operating altitude are fixed, the variation with speed of turbojet thrust and power available is typified by the first graph of figure 2.10. The variation of thrust output with engine speed is a factor of great importance in the operation of the turbojet engine. By reasoning that static pressure changes depend on the square of the flow velocity, the changes of pressure throughout the turbojet engine would be expected to vary as the square of the rotative speed, capital N. However, since a variation in rotative speed will alter airflow, fuel flow, compressor and turbine efficiency, etc., the thrust variation will be much greater than just the square of rotative speed. Instead of thrust being proportional to capital N squared, the typical fixed geometry engine develops thrust approximately proportional to capital N raised to 3.5. Of course, such a variation is particular to constant altitude and speed. Figure 2.10 illustrates the variation of percent maximum thrust with percent maximum RPM for a typical fixed geometry engine. Typical values from this graph are as follows. Percent max RPM, 100, percent max thrust, 100, of course. Percent max RPM, 99, percent max thrust, 96.5. Percent max RPM, 95, percent max thrust, 83.6. Percent max RPM, 90, percent max thrust, 69.2. Percent max RPM, 80, percent max thrust, 45.8. Percent max RPM, 70, percent max thrust, 28.7. Note that in the top end of power output, each 1% RPM change causes a 3.5% change in thrust output. This illustrates the power of variation of thrust with rotative speed which, in this example, is capital N raised to 3.5. Also note that the top 20% of RPM controls more than half of the output thrust. While the fixed geometry engine develops thrust approximately proportional to capital N raised to 3.5, the engine with variable geometry will demonstrate a much more powerful effect of rotative speed. When the jet engine is equipped with a variable nozzle, multi-spool compressor, variable stator blades, etc., the engine is more likely to develop thrust proportional to rotative speed from values of capital N raised to 4.5 to capital N raised to 6.0. For example, if a variable geometry engine develops thrust proportional to capital N raised to 5.0, each 1% RPM change causes a 5.0% thrust change at the top end of power output. Also, the top 13% of RPM would control the top 50% of thrust output. The powerful variation of thrust with engine speed has certain ramifications which should be appreciated. If the turbojet power plant operates at less than the trimmed or adjusted speed for maximum thrust, the deficiency of thrust for takeoff may cause a considerable increase in takeoff distance. During approach, an excessively low RPM may cause very low thrust and produce a very steep glide path. In addition, the low RPM range involves the much greater engine acceleration time to produce thrust for a wave-off. Another complication exists when the thrust is proportional to some large power of rotative speed, e.g., capital N raised to 5.0. The small changes in RPM produce such large variations in thrust that instruments, other than the tachometer, must be furnished for accurate indication of thrust output. The specific fuel consumption, lowercase c sub t, is an important factor for evaluating the performance and efficiency of operation of a turbojet engine. The specific fuel consumption is the proportion between the fuel flow, in pounds per hour, and the thrust, in pounds. For example, an engine which has a fuel flow of 14,000 pounds per hour and a thrust of 12,500 pounds has a specific fuel consumption of lowercase c sub t equals fuel flow over thrust, or lowercase c sub t equals 14,000 pounds per hour over 12,500 pounds, or, lowercase c sub t, equals 1.12 pounds per hour per pound. Thus, each unit pound of thrust requires 1.12 pounds per hour of fuel flow. Obviously, high engine efficiency would be indicated by a low value of lowercase c sub t. Typical values for turbojet engines with relatively high pressure ratios range from 0.8 to 1.2 at design operating conditions in subsonic flight. High energy fuels and greater pressure ratios tend to produce the lower values of lowercase c sub t. Supersonic flight with the attendant inlet losses and high compressor inlet air temperatures tend to increase the specific fuel consumption to values of 1.2 to 2.0. Of course, the use of an afterburner is quite inefficient due to the low combustion pressure, and values of lowercase c sub t, from 2.0 to 4.0 are typical with afterburner operation. The turbojet engine usually has a strong preference for high RPM to produce low specific fuel consumption. Since the normal rated thrust condition is a particular design point for the engine, the minimum value of lowercase c sub t will occur at or near this range of RPM. The illustration of figure 2.10 shows a typical variation of lowercase c sub t with % maximum RPM, where values of RPM less than 80 to 85% produce a specific fuel consumption much greater than the minimum obtainable. This preference for high RPM to obtain low values of lowercase c sub t is very pronounced in the fixed geometry engine. Turbojet engines with multi-spool compressors tend to be less sensitive in this respect, and are more flexible in their operating characteristics. Whenever low values of lowercase c sub t are necessary to obtain range or endurance, the preference of the turbojet engine for the design operating RPM can be a factor of great influence. Altitude is one factor which strongly affects the performance of the turbojet engine. An increase in altitude produces a decrease in density and pressure and, if below the tropopause, a decrease in temperature. If a typical non-afterburning turbojet engine is operated at a constant RPM and true airspeed, the variation of thrust and specific fuel consumption with altitude can be approximated from figure 2.11. The variation of density in the standard atmosphere is shown by the values of density ratio at various altitudes. Typical values of the density ratio at specific altitudes are as follows. Altitude, sea level, density ratio, 1.000. Altitude, 5,000 feet, density ratio, 0.8617. Altitude, 10,000 feet, density ratio, 0.7385. Altitude, 22,000 feet, density ratio, 0.4976. Altitude, 35,000 feet, density ratio, 0.3099. Altitude, 40,000 feet. Density ratio, 0.2462. Altitude, 50,000 feet, density ratio, 0.1532. If the fixed geometry engine is operated at a constant V/TAS, in subsonic flight and constant N RPM, the inlet velocity, inlet ram, and compressor pressure ratio are essentially constant with altitude. An increase in altitude then causes the engine air mass flow to decrease in a manner very nearly identical to the altitude-density ratio. Of course, this decrease in mass flow will produce a significant effect on the output thrust of the engine. Actually, the variation of thrust with altitude is not quite as severe as the density variation because favorable decreases in temperature occur. The decrease in inlet air temperature will provide a relatively greater combustion gas energy and allow a greater jet velocity. The increase in jet velocity somewhat offsets the decrease in mass flow. Of course, an increase in altitude provides lower temperatures below the tropopause. Above the tropopause, no further favorable decrease in temperature takes place, so a more rapid variation of thrust will take place. The approximate variation of thrust with altitude is represented by figure 2.11, and some typical values at specific altitudes are as follows. Altitude, sea level, ratio of thrust at altitude to thrust at sea level, 1.000. Altitude, 5,000 feet, ratio of thrust at altitude to thrust at sea level, 0.888. Altitude, 10,000 feet, ratio of thrust at altitude to thrust at sea level, 0.785. Altitude, 22,000 feet, ratio of thrust at altitude to thrust at sea level, 0.604. Altitude, 35,000 feet, ratio of thrust at altitude to thrust at sea level, 0.392. Altitude, 40,000 feet, ratio of thrust at altitude to thrust at sea level, 0.315. Altitude, 50,000 feet, ratio of thrust at altitude to thrust at sea level, 0.180. Since the change in density with altitude is quite rapid at low altitude, turbojet takeoff performance will be greatly affected at high altitude. Also note that the thrust at 35,000 feet is approximately 39% of the sea level value. The thrust added by the afterburner of a turbojet engine is not affected so greatly by altitude as the basic engine thrust. The use of afterburner may provide a thrust increase of 50% at low altitude or as much as 100% at high altitude. When the inlet ram and compressor pressure ratio is fixed, the principal factor affecting the specific fuel consumption is the inlet air temperature. When the inlet air temperature is lowered, a given heat addition can provide relatively greater changes in pressure or volume. As a result, a given thrust output requires less fuel flow, and the specific fuel consumption, lowercase c sub t, is reduced. While the effect of altitude on specific fuel consumption does not compare with the effect on thrust output, the variation is large enough to strongly influence range and endurance conditions. Figure 2.11 illustrates a typical variation of specific fuel consumption with altitude. Generally, the specific fuel consumption decreases steadily with altitude until the tropopause is reached, and the specific fuel consumption at this point is approximately 80% of the sea level value. Above the tropopause, the temperature is constant, and altitudes slightly above the tropopause cause no further decrease in specific fuel consumption. Actually, altitudes much above the tropopause bring about a general deterioration of overall engine efficiency, and the specific fuel consumption begins an increase with altitude. The extreme altitudes above the tropopause produce low combustion chamber pressures, low compressor Reynolds numbers, low fuel flow, etc., which are not conducive to high engine efficiency. Because of the variation of lowercase c sub t with altitude, the majority of turbojet engines achieve maximum efficiency at or above 35,000 feet. For this reason, the turbojet airplane will find optimum range and endurance conditions at or above 35,000 feet, provided the aircraft is neither thrust limited nor compressibility limited at these altitudes. The governing apparatus of the turbojet engine consists primarily of the items which control the flow of fuel to the engine. In addition, there may be included certain functions which operate variable nozzles, variable stator vanes, variable inlets, etc. Generally, the fuel control and associated items should regulate fuel flow, nozzle area, etc. to provide engine performance scheduled by the throttle or power lever. These regulatory functions provided must account for variations in altitude, temperature, and flight velocity. One principal governing factor which must be available is that a selected power setting, RPM, must be maintained throughout a wide range of flight conditions. Figure 2.12 illustrates the variation of fuel flow with RPM for a turbojet operating at a particular set of flight conditions. Curve 1 depicts the variation with RPM of the fuel flow required for stabilized, steady-state operation of the engine. Each point along this curve 1 defines the fuel flow which is necessary to achieve equilibrium at a given RPM. The steady-state fuel flow produces a turbine power to equal the compressor power requirement at a particular RPM. The throttle position primarily commands a given engine speed, and as changes occur in the ambient pressure, temperature, and flight speed, the steady-state fuel flow will vary. The governing apparatus must account for these variations in flight conditions and maintain the power setting scheduled by throttle position. In addition to the maintenance of steady-state operation, the fuel control and associated engine control items must provide for the transient conditions of engine acceleration and deceleration. In order to accelerate the engine, the fuel control must supply a fuel flow greater than that required for steady-state operation, to produce a turbine power greater than the compressor power requirement. However, the additional fuel flow to accelerate the engine must be controlled and regulated to prevent any one or combination of the following items. 1. Compressor stall or surge. 2. Excessive turbine inlet temperature. 3. Excessively rich fuel-air ratio which may not sustain combustion. Generally, the stall surge and turbine temperature limits predominate to form an acceleration fuel flow boundary typified by curve 2 of figure 2.12. Curve 2 of this illustration defines an upper limit of fuel flow, which can be tolerated within stall surge and temperature limits. The governing apparatus of the engine must limit the acceleration fuel flow within this boundary. To appreciate the governing requirements during the acceleration process, assume the engine described in Figure 2.12 is in steady state, stabilized operation at point A, and it is desired to accelerate the engine to maximum RPM and stabilize at point C. As the throttle is placed at the position for maximum RPM, the fuel control will increase the fuel flow to point B to provide acceleration fuel flow. As the engine accelerates and increases RPM, the fuel control will continue to increase the fuel flow within the acceleration boundary until the engine speed approaches the controlled maximum RPM at point C. As the engine speed nears the maximum at point C, the fuel control will reduce fuel flow to produce stabilized operation at this point and prevent the engine overspeeding the commanded RPM. Of course, if the throttle is opened very gradually, the acceleration fuel flow is barely above the steady state condition, and the engine does not approach the acceleration fuel flow boundary. While this technique is recommended for ordinary conditions, to achieve trouble-free operation and good service life, the engine must be capable of good acceleration to produce rapid thrust changes for satisfactory flight control. In order for the power plant to achieve minimum acceleration times, the fuel control must provide acceleration fuel flow as close as practical to the acceleration boundary. Thus, a maximum controlled acceleration may produce limiting turbine inlet temperatures or slight incipient stall surge of the compressor. Proper maintenance and adjustment of the engine governing apparatus is essential to produce minimum acceleration times without incurring excessive temperatures or heavy stall surge conditions. During deceleration conditions, the minimum allowable fuel flow is defined by the lean limit to support combustion. If the fuel flow is reduced below some critical value at each RPM, lean blowout or flameout will occur. This condition is illustrated by curve 3 of Figure 2.12, which forms the deceleration fuel flow boundary. The governing apparatus must regulate the deceleration fuel flow within this boundary. To appreciate the governing requirements during the deceleration process, assume the engine described in Figure 2.12 is in stabilized, steady-state operation at point C, and it is desired to decelerate to idle conditions and stabilize at point E. As the throttle is placed at the position for idle RPM, the fuel control will decrease the fuel flow to point D to provide the deceleration fuel flow. As the engine decelerates and decreases RPM, the fuel governing will continue to decrease the fuel flow within the deceleration boundary until the idle fuel flow is reached and RPM is established at point E. Of course, if the throttle is closed very slowly, the deceleration fuel flow is barely below the steady state condition, and the engine does not approach the deceleration fuel flow boundary. The fuel control must provide a deceleration flow close to the boundary to provide rapid decrease in thrust and satisfactory flight control. In most cases, the deceleration fuel flow boundary is considerably below the steady-state fuel flow, and no great problem exists in obtaining satisfactory deceleration characteristics. In fact, the greater problem is concerned with obtaining proper acceleration characteristics. For the majority of centrifugal flow engines, the acceleration boundary is set usually by temperature-limiting conditions rather than compressor surge conditions. Peak operating efficiency of the centrifugal compressor is obtained at flow conditions which are below the surge limit, hence acceleration fuel flow boundary is determined by turbine temperature limits. The usual result is that the centrifugal flow engine has relatively large acceleration margins, and good acceleration characteristics result with the low rotational inertia. The axial flow compressor must operate relatively close to the stall surge limit to obtain peak efficiency. Thus, the acceleration fuel flow boundary for the axial flow engine is set by these stall surge limits, which are more immediate to steady state conditions than turbine temperature limits. The fixed geometry axial flow engine encounters relatively small acceleration margins and, when compared to the centrifugal flow engine with larger acceleration margins and lower rotational inertia, has inferior acceleration characteristics. Certain variation of the axial flow engine, such as variable nozzles, variable stator blades, multiple spool compressors, etc., greatly improve the acceleration characteristics. A note of caution is appropriate at this point. If the main fuel control and governing apparatus should malfunction or become inoperative and an unmodulated secondary or emergency system be substituted, extreme care must be taken to avoid abrupt changes in throttle position. In such a case, very gradual movement of the throttle is necessary to accomplish changes in power setting without excessive turbine temperatures, compressor stall, or surge, or flameout. There are various instruments to relate important items of turbojet engine performance. Certain combinations of these instruments are capable of immediately relating the thrust output of the power plant in a qualitative manner. It is difficult to provide an instrument or combination of instruments which immediately relate the thrust output in a quantitative manner. As a result, the pilot must rely on a combination of instrument readings and judge the output performance according to standard values particular to the power plant. Some of the usual engine indicating instruments are as follows. 1. The tachometer provides indication of engine speed, N, by % of the maximum RPM. Since the variation of thrust with RPM is quite powerful, the tachometer indication is a powerful reference. 2. The exhaust gas temperature gauge provides an important reference for engine operating limitations. While the temperature probe may be located downstream from the turbine, tailpipe, or turbine discharge temperature, the instrument should provide an accurate reflection of temperatures upstream in the turbine section. The exhaust gas temperature relates the energy change accomplished by fuel addition. 3. The fuel flow meter can provide a fair reflection of thrust output and operating efficiency. Operation at high density altitude or high inlet air temperatures reduces the output thrust, and this effect is related by a reduction of fuel flow. 4. The tailpipe total pressure, lowercase p plus lowercase q in the tailpipe, can be correlated with the jet thrust for a given engine geometry and set of operating conditions. The output thrust can be related accurately with various combinations of compressor inlet total pressure, tailpipe total pressure, ambient pressure, and temperature. Hence, pressure differential, delta lowercase p, pressure ratio, and tailpipe total pressure instruments can provide more accurate immediate indications of output thrust than combined indications of RPM and EGT. This is especially true with variable geometry or multiple spool engines. Many other specialized instruments furnish additional information for more detailed items of engine performance. Various additional engine information is realized from fuel pressure, nozzle positions, compressor inlet air temperature, etc. Turbojet operating limitations. The operating characteristics of the turbojet engine provide various operating limitations which must be given due respect. Operation of the power plant within the specified limitations is absolutely necessary in order to obtain the designed service life with trouble-free operation. The following items describe the critical areas encountered during the operational use of the turbojet engine. 1. The limiting exhaust gas temperatures provide the most important restrictions to the operation of the turbojet engine. The turbine components are subject to centrifugal loads of rotation, impulse, and reaction loads on the blades, and various vibratory loads which may be inherent with the design. When the turbine components are subject to this variety of stress in the presence of high temperature, two types of structural phenomena must be considered. When a part is subject to a certain stress at some high temperature, weep failure will take place after a period of time. Of course, an increase in temperature or stress will increase the rate at which creep damage is accumulated and reduce the time required to cause failure. Another problem results when a part is subjected to a repeated or cyclic stress. Fatigue failure will occur after a number of cycles of a varying stress. An increase in temperature or magnitude of cyclic stress will increase the rate of fatigue damage and reduce the number of cycles necessary to produce failure. It is important to note that both fatigue and creep damage are cumulative. A gross overstress or overtemperature of the turbine section will produce damage that is immediately apparent. However, the creep and fatigue damage accumulated through periods of less extreme overstress or overtemperature is more subtle. If the turbine is subject to repeated excessive temperatures, the greatly increased rate of creep and fatigue damage will produce failure early within the anticipated service life. Generally, the operations which produce the highest exhaust gas temperatures are starting, acceleration, and maximum thrust at high altitude. The time spent at these temperatures must be limited arbitrarily to prevent excessive accumulation of creep and fatigue. Any time spent at temperatures in excess of the operational limits for these conditions will increase the possibility of early failure of the turbine components. While the turbine components are the most critically stressed high-temperature elements, they are not the only items. The combustion chamber components may be critical at low altitude where high combustion chamber pressures exist. Also, the airframe structure and equipment adjacent to the engine may be subject to quite high temperatures and require provision to prevent damage by excess time at high temperature. 2. The compressor stall or surge has the possibility of producing damaging temperatures in the turbine and combustion chamber or unusual transient loads in the compressor. While the stall surge phenomenon is possible with the centrifugal compressor, the more common occurrence is with the axial flow compressor. Figure 2.13 depicts the pressure distribution that may exist for steady-state operation of the engine. In order to accelerate the engine to a greater speed, more fuel must be added to increase the turbine power above that required to operate the compressor. Suppose that the fuel flow is increased beyond the steady state requirement without a change in rotative speed. The increased combustion chamber pressure due to the greater fuel flow requires that the compressor discharge pressure be higher. For the instant before an engine speed change occurs, an increase in compressor discharge pressure will be accompanied by a decrease in compressor flow velocity. The equivalent effect is illustrated by the flow components onto the rotating compressor blade of Figure 2.13. One component of velocity is due to rotation, and this component remains unchanged for a given rotative velocity of the single blade. The axial flow velocity for steady-state operation combines with the rotational component to define a resultant velocity and direction. If the axial flow component is reduced, the resultant velocity and direction provide an increase in angle of attack for the rotating blade with a subsequent increase in pressure rise. Of course, if the change in angle of attack or pressure rise is beyond some critical value, stall will occur. While the stall phenomenon of a series of rotating compressor blades differs from that of a single airfoil section in a free airstream, the cause and effect are essentially the same. If an excessive pressure rise is required through the compressor, stall may occur with the attendant breakdown of stable, steady flow through the compressor. As stall occurs, the pressure rise drops, and the compressor does not furnish discharge at a pressure equal to the combustion chamber pressure. As a result, a flow reversal or backfire takes place. If the stall is transient and intermittent, the indication will be the intermittent bang as backfire and flow reversal take place. If the stall develops and becomes steady, strong vibration and a loud, and possibly expensive, roar develops from the continuous flow reversal. The increase in compressor power required tends to reduce RPM, and the reduced airflow and increased fuel flow cause rapid, immediate rise in exhaust gas temperature. The possibility of damage is immediate with the steady stall, and recovery must be accomplished quickly by reducing throttle setting, lowering the airplane angle of attack, and increasing airspeed. Generally, the compressor stall is caused by one or a combination of the following items. A malfunctioning fuel control or governing apparatus is a common cause. Proper maintenance and adjustment are a necessity for stall-free operation. The malfunctioning is most usually apparent during engine acceleration. B. Poor inlet conditions are typical at high angles of attack and side slip. These conditions reduce inlet airflow and create non-uniform flow conditions at the compressor face. Of course, these conditions are at the immediate control of the pilot. C. Very high altitude flight produces low compressor Reynolds numbers and an effect similar to that of airfoil sections. As a decrease to low Reynolds numbers reduces the section (CL max), very high altitudes reduce the maximum pressure ratio of the compressor. The reduced stall margins increase the likelihood of compressor stall. Thus, the recovery from a compressor stall must entail reduction of throttle setting to reduce fuel flow, lowering angle of attack and side slip and increasing airspeed to improve inlet conditions, and reducing altitude if high altitude is a contributing factor. 3. While the flameout is a rare occurrence with modern engines, various malfunctions and operating conditions allow the flameout to remain a possibility. A uniform mixture of fuel and air will sustain combustion within a relatively wide range of fuel-air ratios. Combustion can be sustained with a fuel-air ratio as rich as 1:5 or as lean as 1:25. Fuel-air ratios outside these limits will not support combustion due to the deficiency of air or deficiency of fuel. The characteristics of the fuel nozzle and spray pattern as well as the governing apparatus must ensure that the nucleus of combustion is maintained throughout the range of engine operation. If the rich limit of fuel-air ratio is exceeded in the combustion chamber, the flame will blow out. While this condition is a possibility, the more usual cause of a flameout is exceeding the lean blowout limit. Any condition which produces some fuel-air ratio leaner than the lean limit of combustion will produce a flameout. Any interruption of the fuel supply could bring on this condition. Fuel system failure, fuel system icing, or prolonged unusual attitudes could starve the flow of fuel to the engine. It should be noted the majority of aviation fuels are capable of holding in solution a certain small amount of water. If the aircraft is refueled with relatively warm fuel, then flown to high altitude, the lower temperatures can precipitate this water out of solution in liquid or ice crystal form. High-altitude flight produces relatively small air mass flow through the engine, and a relatively low fuel flow rate. At these conditions, a malfunction of the fuel control and governing apparatus could cause flameout. If the fuel control allows excessively low fuel flow during controlled deceleration, the lean blowout limit may be exceeded. Also, if the governed idle condition allows any deceleration below the idle condition, the engine will usually continue to lose speed and flame out. Restarting the engine in flight requires sufficient RPM and airflow to allow stabilized operation. Generally, the extremes of altitude are most critical for attempted air start. 4. An increased compressor inlet air temperature can have a profound effect on the output thrust of a turbojet engine. As shown in Figure 2.13, an increase in compressor inlet temperature produces an even greater increase in the compressor discharge temperature. Since the turbine inlet temperature is limited to some maximum value, any increase in compressor discharge temperature will reduce the temperature change which can take place in the combustion chamber. Hence, the fuel flow will be limited, and a reduction in thrust is incurred. The effect of inlet air temperature on thrust output has two special ramifications. At takeoff, a high ambient air temperature at a given pressure altitude relates a high density altitude. Thus, the takeoff thrust is reduced because of low density and low mass flow. In addition to the loss of thrust due to reduced mass flow, thrust and fuel flow are reduced further because of the high compressor inlet temperature. In flight at high Mach number, the aerodynamic heating will provide an increase in compressor inlet temperature. Since the compressor inlet temperature will reflect the compressor discharge temperature and the allowable fuel flow, the compressor inlet air temperature may provide a convenient limit to sustained high-speed flight. 5. The effect of engine overspeed or critical vibration speed ranges are important in the service life of an engine. One of the principal sources of turbine loads is the centrifugal load due to rotation. Since the centrifugal loads vary as the square of the rotative speed, a 5% overspeed would produce 10.25% overstress, 1.05 squared, equals 1.1025. The large increase in stress with rotative speed could produce very rapid accumulation of creep and fatigue damage at high temperature. Repeated overspeed and, hence, overstress can cause failure early in the anticipated service life. Since the turbojet engine is composed of many different distributed masses and elastic structure, there are certain vibratory modes and frequencies for the shaft, blades, etc. While it is necessary to prevent any resonant conditions from existing within the normal operating range, there may be certain vibratory modes encountered in the low power range common to ground operation, low altitude endurance, acceleration, or deceleration. If certain operating RPM range restrictions are specified due to vibratory conditions, operations must be conducted with a minimum of time in this area. The greatly increased stresses common to vibratory conditions are quite likely to cause fatigue failures of the offending components. The operating limitations of the engine are usually specified by various combinations of RPM, exhaust gas temperature, and allowable time. The conditions of high power output and acceleration have relatively short times allowable to prevent abuse of the power plant and obtain good service life. While the allowable times at various high power and acceleration condition appear arbitrary, the purpose is to reduce the spectrum of loading which contributes the most rapid accumulation of creep and fatigue damage. In fact, in some instances, the arbitrary time standards can be set to suit the particular requirements of a certain type of operation. Of course, the effect on service life of any particular load spectrum must be anticipated. One exception to the arbitrary time standard for operation at high temperatures or sustained high powers is the case of the afterburner operation. When the cooling flow is only that necessary to prevent excessive temperatures for adjacent structure and equipment, sustained operation past a time limit may cause damage to these items. Thrust augmentation. Many operating performance conditions may require that additional thrust be provided for short periods of time. Any means of augmenting the thrust of the turbojet engine must be accomplished without an increase in engine speed or maximum turbine section temperature. The various forms of afterburning or water injection allow the use of additional fuel to provide thrust augmentation without increase in engine speed or turbine temperature. The afterburner is a relatively simple means of thrust augmentation, and the principal features are lightweight and large thrust increase. A typical afterburner installation may add only 10 to 20% of the basic engine weight, but can provide a 40 to 60% increase in the static sea level thrust. The afterburner consists of an additional combustion area aft of the turbine section with an arrangement of fuel nozzles and flame holders. Because the local flow velocities in the afterburner are quite high, the flame holders are necessary to provide the turbulence to maintain combustion within the afterburner section. The turbojet engine operates with airflows greatly in excess of that chemically required to support combustion of engine fuel. This is necessary because of cooling requirements and turbine temperature limitations. Since only 15 to 30% of the engine airflow is used in the combustion chamber, the large excess air in the turbine discharge can support combustion of large amounts of additional fuel. Also, there are no highly stressed, rotating members in the afterburner, and very high temperatures can be tolerated. The combustion of fuel in the afterburner brings additional increase in temperature and volume and adds considerable energy to the exhaust gases, producing increased jet velocity. The major components of the afterburner are illustrated in Figure 2.14. One necessary feature of the turbojet engine equipped with afterburner is a variable nozzle area. As the afterburner begins functioning, the exit nozzle area must increase to accommodate the increased combustion products. If the afterburner were to begin functioning without an increase in exit area, the mass flow through the engine would drop, and the temperatures would increase rapidly. The nozzle area must be controlled to increase as afterburner combustion begins. As a result, the engine mass flow is given a large increase in jet velocity with the corresponding increase in thrust. The combustion of fuel in the afterburner takes place at low pressures and is relatively inefficient. This basic inefficiency of the low-pressure combustion is given evidence by the large increase in specific fuel combustion. Generally, the use of afterburner at least will double the specific fuel consumption. As an example, consider a turbojet engine capable of producing 10,000 pounds of thrust, which can develop 15,000 pounds of thrust with the use of afterburner. Typical values for specific fuel consumption would be lowercase c sub t equals 1.05 for the basic engine, or lowercase c sub t equals 2.1 when the afterburner is in use. The fuel flow during operation would be as follows. Fuel flow equals thrust times specific fuel consumption. Without afterburner, fuel flow equals 10,000 times 1.05, or 10,500 pounds per hour. With afterburner, fuel flow equals 15,000 times 2.1, or 31,500 pounds per hour. The low efficiency of the afterburner is illustrated by the additional 21,000 pounds per hour of fuel flow to create the additional 5,000 pounds of thrust. Because of the high fuel consumption during afterburner operation, and the adverse effect on endurance, the use of the afterburner should be limited to short periods of time. In addition, there may be limited time for the use of the afterburner due to critical heating of supporting or adjacent structure in the vicinity of the afterburner. The specific fuel consumption of the basic engine will increase with the addition of the afterburner apparatus. The losses incurred by the greater fluid friction, nozzle, and flame holder pressure drop, etc. increase the specific fuel consumption of the basic engine approximately 5 to 10%. The principal advantage of afterburner is the ability to add large amounts of thrust with a relatively small weight penalty. The application of the afterburner is most common to the interceptor, fighter, and high-speed type aircraft. The use of water injection in the turbojet engine is another means of thrust augmentation, which allows the combustion of additional fuel within engine speed and temperature limits. The most usual addition of water injection devices is to supplement takeoff and climb-out performance, especially at high ambient temperatures and high altitudes. The typical water injection device can produce a 25 to 35% increase in thrust. The most usual means of water injection is direct flow of the fluid into the combustion chamber. This is illustrated in Figure 2.14. The addition of the fluid directly into the combustion chamber increases the mass flow and reduces the turbine inlet temperature. The drop in temperature reduces the turbine power, and a greater fuel flow is required to maintain engine speed. Thus, the mass flow is increased, more fuel flow is allowed within turbine limits, and greater energy is imparted to the exhaust gases. The fluid injected into the combustion chambers is generally a mixture of water and alcohol. The water-alcohol solution has one immediate advantage in that it prevents fouling of the plumbing from the freezing of residual fluid at low temperatures. In addition, a large concentration of alcohol in the mixture can provide part of the additional chemical energy required to maintain engine speed. In fact, the large concentration of alcohol in the injection mixture is a preferred means of adding additional fuel energy. If the added chemical energy is included with the water flow, no abrupt changes in governed fuel flow are necessary, and there is less chance of underspeed with fluid injection and overspeed or overtemperature when fluid flow is exhausted. Of course, strict proportions of the mixture are necessary. Since most water injection devices are essentially an unmodulated flow, the use of this device is limited to high engine speed and low altitude to prevent the water flow from quenching combustion. The gas turbine-propeller combination. The turbojet engine utilizes the turbine to extract sufficient power to operate the compressor. The remaining exhaust gas energy is utilized to provide the high exhaust gas velocity and jet thrust. The propulsive efficiency of the turbojet engine is relatively low because thrust is produced by creating a large velocity change with a relatively small mass flow. The gas turbine-propeller combination is capable of producing higher propulsive efficiency in subsonic flight by having the propeller operate on a much greater mass flow. The turboprop or propjet power plant requires additional turbine stages to continue expansion in the turbine section and extract a very large percent of the exhaust gas energy as shaft power. In this sense, the turboprop is primarily a power-producing machine, and the jet thrust is a small amount of the output propulsive power. Ordinarily, the jet thrust of the turboprop accounts for 15 to 25% of the total thrust output. Since the turboprop is primarily a power-producing machine, the turboprop power plant is rated by an equivalent shaft horsepower. ESHP equals BHP plus TJ times V over 325 times lowercase eta sub p, where ESHP equals equivalent shaft horsepower, BHP equals brake horsepower or shaft horsepower applied to the propeller, TJ equals jet thrust in pounds, V equals flight velocity in knots true airspeed, and lowercase eta sub p equals propeller efficiency. The gas turbine engine is capable of processing large quantities of air and can produce high output power for a given engine size. Thus, the principal advantage of the turboprop power plant is the high specific power output, high power per engine weight and high power per engine size. The gas turbine engine must operate at quite high rotative speed to process large airflows and produce high power. However, high rotative speeds are not conducive to high propeller efficiency because of compressibility effects. A large reduction of shaft speed must be provided in order to match the power plant and the propeller. The reduction gearing must provide a propeller shaft speed which can be utilized effectively by the propeller end. Because of the high rotative speeds of the turbine, gearing ratios of 6 to 15 may be typical. The transmission of large shaft horsepower with such high gearing involves considerable design problems to provide good service life. The problems of such gearing were one of the greatest difficulties in the development of turboprop power plants. The governing apparatus for the turboprop power plant must account for one additional variable, the propeller blade angle. If the propeller is governed separately from the turbine, an interaction can exist between the engine and propeller governors and various hunting, overspeed, and overtemperature conditions are possible. For this reason, the engine-propeller combination is operated at a constant RPM throughout the major range of output power, and the principal variables of control are fuel flow and propeller blade angle. In the major range of power output, the throttle commands a certain fuel flow, and the propeller blade angle adjusts to increase the propeller load and remain at the governed speed. The operating limitations of the turboprop power plant are quite similar in nature to the operating limitations of the turbojet engine. Generally, the turbine temperature limitations are the most critical items. In addition, overspeed conditions can produce overstress of the gearing and propeller as well as overstress of the turbine section. The performance of the turboprop illustrates the typical advantages of the propeller engine combination. Higher propulsive efficiency and high thrust and low speeds provide the characteristics of range, endurance, and takeoff performance superior to the turbojet. As is typical of all propeller-equipped power plants, the power available is nearly constant with speed. Because the power from the jet thrust depends on velocity, the power available increases slightly with speed. However, the thrust available decreases with speed. The equivalent shaft horsepower, ESHP, of the turboprop is affected by mass flow and inlet temperature in fashion similar to that of the turbojet. Thus, the ESHP will vary with altitude much like the thrust output of the turbojet because the higher altitude produces much lower density and engine mass flow. The gas turbine-propeller combination utilizes a number of turbine stages to extract shaft power from the exhaust gases and, as high compressor inlet temperatures reduce the fuel flow allowable within turbine temperature limits, hot days will cause a noticeable loss of output power. Generally, the turboprop is just as sensitive, if not more sensitive, to compressor inlet air temperature as the turbojet engine. The specific fuel consumption of the turboprop power plant is defined as follows. Specific fuel consumption equals engine fuel flow over equivalent shaft horsepower. Or, lowercase c, equals pounds per hour over ESHP. Typical values for specific fuel consumption, lowercase c, range from 0.5 to 0.8 pounds per hour per ESHP. The variation of specific fuel consumption with operating conditions is similar to that of the turbojet engine. The minimum specific fuel consumption is obtained at relatively high power setting and high altitudes. The low inlet air temperature reduces the specific fuel consumption, and the lowest values of lowercase c are obtained near altitudes of 25,000 to 35,000 feet. Thus, the turboprop as well as the turbojet has a preference for high altitude operation. The reciprocating engine. The reciprocating engine is one of the most efficient power plants used for aircraft power. The combination of the reciprocating engine and propeller is one of the most efficient means of converting the chemical energy of fuel into flying time or distance. Because of the inherent high efficiency, the reciprocating engine is an important type of aircraft power plant. Operating characteristics. The function of the typical reciprocating engine involves 4 strokes of the piston to complete one operating cycle. This principal operating cycle is illustrated in Figure 2.15 by the variation of pressure and volume within the cylinder. The first stroke of the operating cycle is the downstroke of the piston with the intake valve open. This stroke draws in a charge of fuel air mixture along A, B of the pressure volume diagram. The second stroke accomplishes compression of the fuel air mixture along line BC. Combustion is initiated by a spark ignition apparatus, and combustion takes place in essentially a constant volume. The combustion of the fuel air mixture liberates heat, and causes the rise of pressure along line CD. The power stroke utilizes the increased pressure through the expansion along line DE. Then the exhaust begins by the initial rejection along line EB and is completed by the upstroke along line BA. The net work produced by the cycle of operation is idealized by the area BCDE on the pressure volume diagram of Figure 2.15. During the actual rather than ideal cycle of operation, the intake pressure is lower than the exhaust pressure, and the negative work represents a pumping loss. The incomplete expansion during the power stroke represents a basic loss in the operating cycle because of the rejection of combustion products along line EB. The area EFB represents a certain amount of energy of the exhaust gases, a part of which can be extracted by exhaust turbines as additional shaft power to be coupled to the crankshaft, turbo compound engine, or to be used in operating a supercharger, turbosupercharger. In addition, the exhaust gas energy may be utilized to augment engine cooling flow, ejector exhaust, and reduce cowl drag. Since the net work produced during the operating cycle is represented by the enclosed area of the pressure volume diagram, the output of the engine is affected by any factor which influences this area. The weight of fuel air mixture will determine the energy released by combustion, and the weight of charge can be altered by altitude, supercharging, etc. Mixture strength, pre-ignition, spark timing, etc., can affect the energy release of a given airflow and alter the work produced during the operating cycle. The mechanical work accomplished during the power stroke is the result of the gas pressure sustained on the piston. The linkage of the piston to a crankshaft by the connecting rod applies torque to the output shaft. During this conversion of pressure energy to mechanical energy, certain losses are inevitable because of friction, and the mechanical output is less than the available pressure energy. The power output from the engine will be determined by the magnitude and rate of the power impulses. In order to determine the power output of the reciprocating engine, a brake or load device is attached to the output shaft, and the operating characteristics are determined. Hence, the term brake horsepower, bhp, is used to denote the output power of the power plant. From the physical definition of power, and the particular unit of horsepower, 1 horsepower, equals 33,000 foot-pounds per minute, the brake horsepower can be expressed in the following form. bhp equals 2 pi times T times capital N over 33,000, or bhp equals T times capital N over 5,255. Where bhp equals brake horsepower, T equals output torque in foot-pounds, and N equals output shaft speed in RPM. In this relationship, the output power is appreciated as some direct variable of torque, T, and RPM. Of course, the output torque is some function of the combustion gas pressure during the power stroke. Thus, it is helpful to consider the mean effective gas pressure during the power stroke, the brake mean effective pressure, or BMEP. With use of this term, the BHP can be expressed in the following form. BHP equals BMEP times D times capital N over 792,000. Where BHP equals brake horsepower. BMEP equals brake mean effective pressure in pounds per square inch, D equals engine displacement in cubic inches, and N equals engine speed in RPM. The BMEP is not actual pressure within the cylinder, but an effective pressure representing the mean gas load acting on the piston during the power stroke. As such, BMEP is a convenient index for a majority of items of reciprocating engine output, efficiency, and operating limitations. The actual power output of any reciprocating engine is a direct function of the combination of engine torque and rotative speed. Thus, output brake horsepower can be related by the combination of BMEP and RPM, or torque pressure and RPM. No other engine instruments can provide this immediate indication of output power. If all other factors are constant, the engine power output is directly related to the engine airflow. Evidence of this fact could be appreciated from the equation for BHP in terms of BMEP. BHP equals BMEP times D times capital N over 792,000. This equation relates that, for a given BMEP, the BHP is determined by the product of engine RPM, capital N, and displacement, D. In a sense, the reciprocating engine could be considered primarily as an air pump with the pump capacity directly affecting the power output. Thus, any engine instruments which relate factors affecting airflow can provide some indirect reflection of engine power. The pressure and temperature of the fuel-air mixture decide the density of the mixture entering the cylinder. The carburetor air temperature will provide the temperature of the inlet air at the carburetor. While this carburetor inlet air is not the same temperature as the air in the cylinder inlet manifold, the carburetor inlet temperature provides a stable indication independent of fuel flow and can be used as a standard of performance. Cylinder inlet manifold temperature is difficult to determine with the same degree of accuracy because of the normal variation of fuel-air mixture strength. The inlet manifold pressure provides an additional indication of the density of airflow entering the combustion chamber. The manifold absolute pressure, MAP, is affected by the carburetor inlet pressure, throttle position, and supercharger or impeller pressure ratio. Of course, the throttle is the principal control of manifold pressure, and the throttling action controls the pressure of the fuel-air mixture delivered to the supercharger inlet. The pressure received by the supercharger is magnified by the supercharger in some proportion depending on impeller speed. Then the high-pressure mixture is delivered to the manifold. Of course, the engine airflow is a function of RPM for two reasons. A higher engine speed increases the pumping rate, and the volume flow through the engine. Also, with the engine-driven supercharger or impeller, an increase in engine speed increases the supercharger pressure ratio. With the exception of near-closed throttle position, an increase in engine speed will produce an increase in manifold pressure. The many variables affecting the character of the combustion process are an important subject of reciprocating engine operation. Uniform mixtures of fuel and air will support combustion between fuel-air ratios of approximately 0.04 and 0.20. The chemically correct proportions of air and hydrocarbon fuel would be 15 pounds of air for each pound of fuel, or a fuel-air ratio of 0.067. This chemically correct, or stoichiometric, fuel-air ratio would provide the proportions of fuel and air to produce maximum release of heat during combustion of a given weight of mixture. If the fuel-air ratio were leaner than stoichiometric, the excess of air and deficiency of fuel would produce lower combustion temperatures and reduced heat release for a given weight of charge. If the fuel-air ratio were richer than stoichiometric, the excess of fuel and deficiency of air would produce lower combustion temperatures and reduced heat release for a given weight of charge. The stoichiometric conditions would produce maximum heat release for ideal conditions of combustion, and may apply quite closely for the individual cylinders of the low-speed reciprocating engine. Because of the effects of flame propagation speed, fuel distribution, temperature variation, etc., the maximum power obtained with a fixed airflow occurs at fuel-air ratios of approximately 0.07 to 0.08. The first graph of figure 2.16 shows the variation of output power with fuel-air ratio for a constant engine airflow, i.e., constant RPM, MAP, and CAT, carburetor air temperature, combustion can be supported by fuel-air ratios just greater than 0.04, but the energy released is insufficient to overcome pumping losses and engine mechanical friction. Essentially, the same result is obtained for the rich fuel-air ratios just below 0.20. Fuel-air ratios between these limits produce varying amounts of output power, and the maximum power output generally occurs at fuel-air ratios of approximately 0.07 to 0.08. Thus, this range of fuel-air ratios which produces maximum power for a given airflow is termed the best power range. At some lower range of fuel-air ratios, a maximum of power per fuel-air ratio is obtained, and this is the best economy range. The best economy range generally occurs between fuel-air ratios of 0.05 and 0.07. When maximum engine power is required for takeoff, fuel-air ratios greater than 0.08 are necessary to suppress detonation. Hence, fuel-air ratios of 0.09 to 0.11 are typical during this operation. The pattern of combustion in the cylinder is best illustrated by the second graph of figure 2.16. The normal combustion process begins by spark ignition toward the end of the compression stroke. The electric spark provides the beginning of combustion, and a flame front is propagated smoothly through the compressed mixture. Such normal combustion is shown by the plot of cylinder pressure versus piston travel. Spark ignition begins a smooth rise of cylinder pressure to some peak value with subsequent expansion through the power stroke. The variation of pressure with piston travel must be controlled to achieve the greatest net work during the cycle of operation. Obviously, spark ignition timing is an important factor controlling the initial rise of pressure in the combustion chamber. The ignition of the fuel mixture must begin at the proper time to allow flame front propagation, and the release of heat to build up peak pressure for the power stroke. The speed of flame front propagation is a major factor affecting the power output of the reciprocating engine, since this factor controls the rate of heat release and rate of pressure rise in the combustion chamber. For this reason, dual ignition is necessary for power plants of high specific power output. Obviously, normal combustion can be accomplished more rapidly with the propagation of two flame fronts rather than one. The two sources of ignition are able to accomplish the combustion heat release and pressure rise in a shorter period of time. Fuel-air ratio is another factor affecting the flame propagation speed in the combustion chamber. The maximum flame propagation speed occurs near a fuel-air ratio of 0.08 and, thus, maximum power output for a given airflow will tend to occur at this value rather than the stoichiometric value. Two aberrations of the combustion process are pre-ignition and detonation. Pre-ignition is simply a premature ignition and flame front propagation due to hot spots in the combustion chamber. Various lead and carbon deposits and feathered edges on metal surfaces can supply a glow ignition spot and begin a flame propagation prior to normal spark ignition. As shown on the graph of figure 2.16, pre-ignition causes a premature rise of pressure during the piston travel. As a result, pre-ignition combustion pressures and temperatures will exceed normal combustion values and are very likely to cause engine damage. Because of the premature rise of pressure toward the end of the compression stroke, the net work of the operating cycle is reduced. Pre-ignition is evidenced by a rise in cylinder head temperature and drop in BMEP or torque pressure. Detonation offers the possibility of immediate destruction of the power plant. The normal combustion process is initiated by the spark and beginning of flame front propagation. As the flame front is propagated, the combustion chamber pressure and temperature begin to rise. Under certain conditions of high combustion pressure and temperature, the mixture ahead of the advancing flame front may suddenly explode with considerable violence and send strong detonation waves through the combustion chamber. The result is depicted by the graph of figure 2.16, where a sharp, explosive increase in pressure takes place with a subsequent reduction of the mean pressure during the power stroke. Detonation produces sharp explosive pressure peaks many times greater than normal combustion. Also, the exploding gases radiate considerable heat and cause excessive temperatures for many local parts of the engine. The effects of heavy detonation are so severe that structural damage is the immediate result. Rapid rise of cylinder head temperature, rapid drop in BMEP, and loud, expensive noises are evidence of detonation. Detonation is not necessarily confined to a period after the beginning of normal flame front propagation. With extremely low grades of fuel, detonation can occur before normal ignition. In addition, the high temperatures and pressure caused by pre-ignition will mean that detonation is usually a corollary of pre-ignition. Detonation results from a sudden, unstable decomposition of fuel at some critical combination of high temperature and pressure. Thus, detonation is most likely to occur at any operating condition which produces high combustion pressures and temperatures. Generally, high engine airflow and fuel-air ratios for maximum heat release will produce the critical conditions. High engine airflow is common to high M, A, P, and RPM, and the engine is most sensitive to C, A, T, and fuel-air ratio in this region. The detonation properties of a fuel are determined by the basic molecular structure of the fuel and the various additives. The fuel detonation properties are generally specified by the anti-detonation or anti-knock qualities of an octane rating. Since the anti-knock properties of a high-quality fuel may depend on the mixture strength, provision must be made in the rating of fuels. Thus, a fuel grade of 115-145 would relate a lean mixture anti-knock rating of 115 and a rich mixture anti-knock rating of 145. One of the most common operational causes of detonation is fuel contamination. An extremely small contamination of high-octane fuel with jet fuel can cause a serious decrease in the anti-knock rating. Also, the contamination of a high-grade fuel with the next lower grade will cause a noticeable loss of anti-knock quality. The fuel metering requirements for an engine are illustrated by the third graph of Figure 2.16, which is a plot of fuel-air ratio versus engine airflow. The carburetor must provide specific fuel-air ratios throughout the range of engine airflow to accommodate certain output power. Most modern engines equipped with automatic mixture control provide a scheduling of fuel-air ratio for auto-rich or auto-lean operation. The auto-rich scheduling usually provides a fuel-air ratio at or near the maximum heat release value for the middle range of airflows. However, at high airflows a power enrichment must be provided to suppress detonation. The auto-rich schedule generally will provide an approximate fuel-air ratio of 0.08 which increases to 0.10 or 0.11 at the airflow for takeoff power. In addition, the low airflow and mixture dilution that occurs in the idle power range requires enrichment for satisfactory operation. The schedule of fuel-air ratios with an automatic lean fuel-air ratio will automatically provide maximum usable economy. If manual leaning procedures are applicable, a lower fuel-air ratio may be necessary for maximum possible efficiency. The maximum continuous cruise power is the upper limit of power that can be utilized for this operation. Higher airflows and higher power without a change in fuel-air ratio will intersect the knee of the detonation envelope. The primary factor relating the efficiency of operation of the reciprocating engine is the brake-specific fuel consumption, BSFC, or simply lowercase c. Brake-specific fuel consumption equals engine fuel flow over brake horsepower, where lowercase c equals pounds per hour per brake horsepower. Typical minimum values for lowercase c range from 0.4 to 0.6 pounds per hour per bhp, and most aircraft power plants average 0.5. The turbo-compound engine is generally the most efficient, because of the power recovery turbines, and can approach values of lowercase c equals 0.38 to 0.42. It should be noted that the minimum values of specific fuel consumption will be obtained only within the range of cruise power operation, 30 to 60% of the maximum power output. Generally, the conditions of minimum specific fuel consumption are achieved with auto-lean or manual lean scheduling of fuel-air ratios and high BMEP and low RPM. The low RPM is the usual requirement to minimize friction horsepower and improve output efficiency. The effect of altitude is to reduce the engine airflow and power output, and supercharging is necessary to maintain high power output at high altitude. Since the basic engine is able to process air only by the basic volume displacement, the function of the supercharger is to compress the inlet air and provide a greater weight of air for the engine to process. Of course, shaft power is necessary to operate the engine-driven supercharger, and a temperature rise occurs through the supercharger compression. The effect of various forms of supercharging on altitude performance is illustrated in Figure 2.17. The unsupercharged or naturally aspirated engine has no means of providing a manifold pressure any greater than the induction system inlet pressure. As altitude is increased with full throttle and a governed RPM, the airflow through the engine is reduced and bhp decreases. The first forms of supercharging were of relatively low pressure ratio, and the added airflow and power could be handled at full throttle within detonation limits. Such a ground-boosted engine would achieve higher output power at all altitudes, but an increase in altitude would produce a decrease in manifold pressure, airflow, and power output. More advanced forms of supercharging with higher pressure ratios can produce very large engine airflow. In fact, the typical case of altitude supercharging will produce such high airflow at low altitude operation that full throttle operation cannot be utilized within detonation limits. Figure 2.17 illustrates this case for a typical two-speed engine-driven altitude supercharging installation. At sea level, the limiting manifold pressure produces a certain amount of bhp. Full throttle operation could produce a higher MAP and bhp if detonation were not the problem. In this case, full throttle operation is unavailable because of detonation limits. As altitude is increased with the supercharger or blower at low speed, the constant MAP is maintained by opening the throttle, and the bhp increases above the sea level value because of the reduced exhaust back pressure. Opening the throttle allows the supercharger inlet to receive the same inlet pressure and produce the same MAP. Finally, the increase of altitude will require full throttle to produce the constant MAP with low blower, and this point is termed the critical altitude or full throttle height. If altitude is increased beyond the critical altitude, the engine MAP, airflow, and bhp decrease. The critical altitude with a particular supercharger installation is specific to a given combination of MAP and RPM. Obviously, a lower MAP could be maintained to some higher altitude, or a lower engine speed would produce less supercharging, and a given MAP would require a greater throttle opening. Generally, the most important critical altitudes will be specified for maximum, rated, and maximum cruise power conditions. A change of the blower to a high speed will provide greater supercharging, but will require more shaft power and incur a greater temperature rise. Thus, the high blower speed can produce an increase in altitude performance within the detonation limitations. The variation of bhp with altitude for the blower at high speed shows an increase in critical altitude, and greater bhp than is obtainable in low blower. Operation below the high blower critical altitude requires some limiting manifold pressure to remain within detonation limits. It is apparent that the shift to high blower is not required just past low blower critical altitude, but at the point where the transition from low blower, full throttle to high blower, limit MAP will produce greater bhp. Of course, if the blower speed is increased without reducing the throttle opening, an overboost can occur. Since the exhaust gases have considerable energy, exhaust turbines provide a source of supercharger power. The turbosupercharger, TBS, allows control of the supercharger speed and output to very high altitudes with a variable discharge exhaust turbine, VDT. The turbosupercharger is capable of providing the engine airflow with increasing altitude by increasing turbine and supercharger speed. Critical altitude for the turbosupercharger is usually defined by the altitude which produces the limiting exhaust turbine speed. The minimum specific fuel consumption of the supercharged engine is not greatly affected by altitudes less than the critical altitude. At the maximum cruise power condition, specific fuel consumption will decrease slightly with an increase in altitude up to the critical altitude. Above critical altitude, maximum cruise power cannot be maintained, but the specific fuel consumption is not adversely affected as long as auto lean or manual lean power can be used at the cruise power setting. One operating characteristic of the reciprocating engine is distinctly different from that of the turbojet. Water vapor in the air will cause a significant reduction in output power of the reciprocating engine, but a negligible loss of thrust for the turbojet engine. This basic difference exists because the reciprocating engine operates with a fixed displacement, and all air processed is directly associated with the combustion process. If water vapor enters the induction system of the reciprocating engine, the amount of air available for combustion is reduced and, since most carburetors do not distinguish water vapor from air, an enrichment of the fuel-air ratio takes place. The maximum power output at takeoff requires fuel-air ratios richer than that for maximum heat release, so a further enrichment will take place with subsequent loss of power. The turbojet operates with such great excess of air that the combustion process essentially is unaffected, and the reduction of air mass flow is the principal consideration. As an example, extreme conditions which would produce high specific humidity may cause a 3% thrust loss for a turbojet, but a 12% loss of bhp for a reciprocating engine. Proper accounting of the loss due to humidity is essential in the operation of the reciprocating engine. Operating limitations. Reciprocating engines have achieved a great degree of refinement and development, and are one of the most reliable of all types of aircraft power plants. However, reliable operation of the reciprocating engine is obtained only by strict adherence to the specific operating limitations. The most important operating limitations of the reciprocating engine are those provided to ensure that detonation and pre-ignition do not take place. The pilot must ensure that proper fuel grades are used and that MAP, BMEP, RPM, CAT, etc. limitations are not exceeded. Since heavy detonation or pre-ignition is common to the high airflow at maximum power, the most likely chance of detonation or pre-ignition is at takeoff. In order to suppress detonation or allow greater power for takeoff, water injection is often used in the reciprocating engine. At high power settings, the injection of the water-alcohol mixture can replace the excess fuel required to suppress detonation, and derichment provisions can reduce the fuel-air ratio toward the value for maximum heat release. Thus, an increase in power will be obtained by the better fuel-air ratio. In some instances, a higher manifold pressure can be utilized to produce additional power. The injection fluid will require proportions of alcohol and water quite different from the injection fluid for jet engine thrust augmentation. Since derichment of the fuel-air ratio is desired, the anti-detonation injection, ADI, will contain alcohol in quantities to prevent residual fluid from fouling the plumbing. When the fuel grades are altered during operation, and the engine must be operated on a next lower fuel grade, proper account must be made for the change in the operating limitations. This accounting must be made for the maximum power for takeoff and the maximum cruise power, since both of these operating conditions are near the detonation envelope. In addition, when the higher grade of fuel again becomes available, the higher operating limits cannot be used until it is sure that no contamination exists from the lower grade fuel remaining in the tanks. Spark plug fouling can provide certain high as well as low limits of operating temperatures. When excessively low operating temperatures are encountered, rapid carbon fouling of the plugs will take place. On the other hand, excessively high operating temperatures will produce plug fouling from lead bromide deposits from the fuel additives. Generally, the limited periods of time at various high power settings are set to minimize the accumulation of high rates of wear and fatigue damage. By minimizing the amount of total time spent at high power setting, greater overhaul life of the power plant can be achieved. This should not imply that the takeoff rating of the engine should not be used. Actually, the use of the full maximum power at takeoff will accumulate less total engine wear than a reduced power setting at the same RPM because of less time required to climb to a given altitude or to accelerate to a given speed. The most severe rate of wear and fatigue damage occurs at high RPM and low MAP. High RPM produces high centrifugal loads and reciprocating inertia loads. When the large reciprocating inertia loads are not cushioned by high compression pressures, critical resultant loads can be produced. Thus, operating time at maximum RPM and MAP must be held to a minimum, and operation at maximum RPM and low MAP must be avoided. Aircraft propellers. The aircraft propeller functions to convert the power plant shaft horsepower into propulsive horsepower. The basic principles of propulsion apply to the propeller in that thrust is produced by providing the airstream a momentum change. The propeller achieves high propulsive efficiency by processing a relatively large mass flow of air and imparting a relatively small velocity change. The momentum change created by the propeller is shown by the illustration of Figure 2.18. The action of the propeller can be idealized by the assumption that the rotating propeller is simply an actuating disc. As shown in Figure 2.18, the inflow approaching the propeller disc indicates converging streamlines with an increase in velocity and drop in pressure. The converging streamlines leaving the propeller disc indicate a drop in pressure and increase in velocity behind the propeller. The pressure change through the disc results from the distribution of thrust over the area of the propeller disc. In this idealized propeller disc, the pressure difference is uniformly distributed over the disc area, but the actual case is rather different from this. The final velocity of the propeller slipstream, V sub 2, is achieved some distance behind the propeller. Because of the nature of the flow pattern produced by the propeller, 1/2 of the total velocity change is produced as the flow reaches the propeller disc. If the complete velocity increase amounts to 2a, the flow velocity has increased by the amount a at the propeller disc. The propulsive efficiency of the ideal propeller could be expressed by the following relationship. Lowercase eta sub p equals output power over input power. lowercase eta sub p equals TV over T times the quantity V plus A, where lowercase eta sub p equals propulsive efficiency, T equals thrust in pounds, V equals flight velocity in knots, and A equals velocity increment at the propeller disc in knots. Since the final velocity, V sub 2, is the sum of total velocity change 2A, and the initial velocity, V sub 1, the propulsive efficiency rearranges to a form identical to that for the turbojet. Lowercase eta sub p equals 2 over 1 plus the quantity V sub 2 over V sub 1. So, the same relationship exists as with the turbojet engine in that high efficiency is developed by producing thrust with the highest possible mass flow and smallest necessary velocity change. The actual propeller must be evaluated in a more exact sense to appreciate the effect of non-uniform disc loading, propeller blade drag forces, interference flow between blades, etc. With these differences from the ideal propeller, it is more appropriate to define propeller efficiency in the following manner. Lowercase eta sub p equals output propulsive power over input shaft horsepower. Lowercase eta sub p equals T times V over 325 times bhp, where lowercase eta sub p equals propeller efficiency, T equals propeller thrust, V equals flight velocity in knots, and bhp equals brake horsepower applied to the propeller. Many different factors govern the efficiency of a propeller. Generally, a large diameter propeller favors a high propeller efficiency from the standpoint of large mass flow. However, a powerful adverse effect on propeller efficiency is produced by high tip speeds and compressibility effects. Of course, small diameter propellers favor low tip speeds. In addition, the propeller and power plant must be matched for compatibility of output and efficiency. In order to appreciate some of the principal factors controlling the efficiency of a given propeller, Figure 2.18 illustrates the distribution of rotative velocity along the rotating propeller blade. These rotative velocities add to the local inflow velocities to produce a variation of resultant velocity and direction along the blade. The typical distribution of thrust along the propeller blade is shown with the predominating thrust being located on the outer portions of the blade. Note that the propeller producing thrust develops a tip vortex similar to the wing producing lift. Evidence of this vortex can be seen by the condensation phenomenon occurring at this location under certain atmospheric conditions. The component velocities at a given propeller blade section are shown by the diagram of Figure 2.18. The inflow velocity adds vectorially to the velocity due to rotation to produce an inclination of the resultant wind with respect to the plane of rotation. This inclination is termed lowercase v, the effective pitch angle, and is a function of some proportion of the flight velocity, v, and the velocity due to rotation, which is pi times lowercase n times d at the tip. The proportions of these terms describe the propeller advance ratio, capital J, where capital J equals propeller advance ratio, V equals flight velocity in feet per second, lowercase n equals propeller rotative speed in revolutions per second, and d equals propeller diameter in feet. The propeller blade angle, lowercase beta, varies throughout the length of the blade, but a representative value is measured at 75% of the blade length from the hub. Note that the difference between the effective pitch angle, lowercase v, and the blade angle, lowercase beta, determines an effective angle of attack for the propeller blade section. Since the angle of attack is the principal factor affecting the efficiency of an airfoil section, it is reasonable to make the analogy that the advance ratio, capital J, and blade angle, lowercase beta, are the principal factors affecting propeller efficiency. The performance of a propeller is typified by the chart of Figure 2.19, which illustrates the variation of propeller efficiency, lowercase eta sub p, with advance ratio, capital J, for various values of blade angle, lowercase beta. The value of lowercase eta sub p for each lowercase beta increases with capital J until a peak is reached, then decreases. It is apparent that a fixed-pitch propeller may be selected to provide suitable performance in a narrow range of advance ratio, but efficiency would suffer considerably outside this range. In order to provide high propeller efficiency through a wide range of operation, the propeller blade angle must be controllable. The most convenient means of controlling the propeller is the provision of a constant speed governing apparatus. The constant speed governing feature is favorable from the standpoint of engine operation in that engine output and efficiency is positively controlled and governed. The governing of the engine-propeller combination will allow operation throughout a wide range of power and speed while maintaining efficient operation. If the envelope of maximum propeller efficiency is available, the propulsive horsepower available will appear as shown in the second chart of Figure 2.19. The propulsive power available, PA, is the product of the propeller efficiency and applied shaft horsepower. PA equals TV over 325, or PA equals lowercase eta sub p times bhp. The propellers used on most large reciprocating engines derive peak propeller efficiencies on the order of lowercase eta sub p equals 0.85 to 0.88. Of course, the peak values are designed to occur at some specific design condition. For example, the selection of a propeller for a long-range transport would require matching of the engine-propeller combination for peak efficiency at cruise condition. On the other hand, selection of a propeller for a utility or liaison-type airplane would require matching of the engine-propeller combination to achieve high propulsive power at low speed and high power for good takeoff and climb performance. Several special considerations must be made for the application of aircraft propellers. In the event of a power plant malfunction or failure, provision must be made to streamline the propeller blades and reduce drag so that flight may be continued on the remaining operating engines. This is accomplished by feathering the propeller blades, which stops rotation and incurs a minimum of drag for the inoperative engine. The necessity for feathering is illustrated in Figure 2.19 by the change in equivalent parasite area, delta F, with propeller blade angle, lowercase beta, of a typical installation. When the propeller blade angle is in the feathered position, the change in parasite drag is at a minimum and, in the case of a typical multi-engine aircraft, the added parasite drag from a single feathered propeller is a relatively small contribution to the airplane total drag. At smaller blade angles, the drag added by the propeller is very large. At these small blade angles, the propeller windmilling at high RPM can create such a tremendous amount of drag that the airplane may be uncontrollable. The propeller windmilling at high speed in the low range of blade angles can produce an increase in parasite drag which may be as great as the parasite drag of the basic airplane. An indication of this powerful drag is seen by the helicopter in autorotation. The windmilling rotor is capable of producing autorotation rates of descent which approach that of a parachute canopy with the identical disk area loading. Thus, the propeller windmilling at high speed and small blade angle can produce an effective drag coefficient of the disk area which compares with that of a parachute canopy. The drag and yawing moment caused by loss of power at high engine propeller speed is considerable, and the transient yawing displacement of the aircraft may produce critical loads for the vertical tail. For this reason, automatic feathering may be a necessity rather than a luxury. The large drag which can be produced by the rotating propeller can be utilized to improve the stopping performance of the airplane. Rotation of the proper blade to small positive values or negative values with applied power can produce large drag or reverse thrust. Since the thrust capability of the propeller is quite high at low speeds, very high deceleration can be provided by reverse thrust alone. The operating limitations of the propeller are closely associated with those of the power plant. Overspeed conditions are critical because of the large centrifugal loads and blade twisting moments produced by an excessive rotative speed. In addition, the propeller blades will have various vibratory modes, and certain operating limitations may be necessary to prevent exciting resonant conditions. Items of airplane performance. The various items of airplane performance result from the combination of airplane and power plant characteristics. The aerodynamic characteristics of the airplane generally define the power and thrust requirements at various conditions of flight, while the power plant characteristics generally define the power and thrust available at various conditions of flight. The matching of the aerodynamic configuration with the power plant will be accomplished to provide maximum performance at the specific design condition, e.g., range, endurance, climb, etc. Straight and level flight. When the airplane is in steady, level flight, the condition of equilibrium must prevail. The unaccelerated condition of flight is achieved with the airplane trimmed for lift equal to weight, and the power plant set for a thrust to equal the airplane drag. In certain conditions of airplane performance, it is convenient to consider the airplane requirements by the thrust required, or drag, while in other cases it is more applicable to consider the power required. Generally, the jet airplane will require consideration of the thrust required, and the propeller airplane will require consideration of the power required. Hence, the airplane in steady level flight will require lift equal to weight and thrust available equal to thrust required, drag, or power available equal to power required. The variation of power required and thrust required with velocity is illustrated in Figure 2.20. Each specific curve of power or thrust required is valid for a particular aerodynamic configuration at a given weight and altitude. These curves define the power or thrust required to achieve equilibrium, lift equal weight, constant altitude flight at various airspeeds. As shown by the curves of Figure 2.20, if it is desired to operate the airplane at the airspeed corresponding to point A, the power or thrust required curves define a particular value of thrust or power that must be made available from the power plant to achieve equilibrium. Some different airspeed, such as that corresponding to point B, changes the value of thrust or power required to achieve equilibrium. Of course, the change of airspeed to point B also would require a change in angle of attack to maintain a constant lift equal to the airplane weight. Similarly, to establish airspeed and achieve equilibrium at point C will require a particular angle of attack and power plant thrust or power. In this case, flight at point C would be in the vicinity of the minimum flying speed, and a major portion of the thrust or power required would be due to induced drag. The maximum level flight speed for the airplane will be obtained when the power or thrust required equals the maximum power or thrust available from the power plant. The minimum level flight airspeed is not usually defined by thrust or power requirement, since conditions of stall or stability and control problems generally predominate. Climb performance. During climbing flight, the airplane gains potential energy by virtue of elevation. This increase in potential energy during a climb is provided by one, or a combination, of two means. 1. Expenditure of propulsive energy above that required to maintain level flight, or 2. Expenditure of airplane kinetic energy, i.e., loss of velocity by a zoom. Zooming for altitude is a transient process of trading kinetic energy for potential energy and is of considerable importance for airplane configurations which can operate at very high levels of kinetic energy. However, the major portion of climb performance for most airplanes is a near-steady process in which additional propulsive energy is converted into potential energy. The fundamental parts of airplane climb performance involve a flight condition where the airplane is in equilibrium, but not at constant altitude. The forces acting on the airplane during a climb are shown by the illustration of Figure 2.21. When the airplane is in steady flight with moderate angle of climb, the vertical component of lift is very nearly the same as the actual lift. Such climbing flight would exist with the lift very nearly equal to the weight. The net thrust of the power plant may be inclined relative to the flight path, but this effect will be neglected for the sake of simplicity. Note that the weight of the aircraft is vertical, but a component of weight will act aft along the flight path. If it is assumed that the aircraft is in a steady climb with essentially small inclination of the flight path, the summation of forces along the flight path resolves to the following. Forces forward equals forces aft. T equals D plus W times sine lowercase gamma. Where T equals thrust available in pounds, D equals drag in pounds, W equals weight in pounds, and lowercase gamma equals flight path inclination or angle of climb in degrees. This basic relationship neglects some of the factors which may be of importance for airplanes of very high climb performance. For example, a more detailed consideration would account for the inclination of thrust from the flight path, lift not equal to weight, subsequent change of induced drag, etc. However, this basic relationship will define the principal factors affecting climb performance. With this relationship established by the condition of equilibrium, the following relationship exists to express the trigonometric sign of the climb angle, lowercase gamma. Sine lowercase gamma equals T minus D over W. This relationship simply states that, for a given weight airplane, the angle of climb, lowercase gamma, depends on the difference between thrust and drag, T minus D, or excess thrust. Of course, when the excess thrust is 0, T minus D equals 0, or T equals D, the inclination of the flight path is 0, and the airplane is in steady, level flight. When the thrust is greater than the drag, the excess thrust will allow a climb angle depending on the value of excess thrust. Also, when the thrust is less than the drag, the deficiency of thrust will allow an angle of descent. The most immediate interest in the climb angle performance involves obstacle clearance. The maximum angle of climb would occur where there exists the greatest difference between thrust available and thrust required, i.e., maximum, T minus D. Figure 2.21 illustrates the climb angle performance with the curves of thrust available and thrust required versus velocity. The thrust required, or drag curve, is assumed to be representative of some typical airplane configuration which could be powered by either a turbojet or propeller-type powerplant. The thrust available curves included are for a characteristic propeller powerplant and jet powerplant operating at maximum output. The thrust curves for the representative propeller aircraft show the typical propeller thrust, which is high at low velocities and decreases with an increase in velocity. For the propeller-powered airplane, the maximum excess thrust and angle of climb will occur at some speed just above the stall speed. Thus, if it is necessary to clear an obstacle after takeoff, the propeller-powered airplane will attain maximum angle of climb at an airspeed conveniently close to, if not at, the takeoff speed. The thrust curves for the representative jet aircraft show the typical turbojet thrust, which is very nearly constant with speed. If the thrust available is essentially constant with speed, the maximum excess thrust and angle of climb will occur where the thrust required is at a minimum, L/D max. Thus, for maximum steady-state angle of climb, the turbojet aircraft would be operated at the speed for L/D max. This poses somewhat of a problem in determining the proper procedure for obstacle clearance after takeoff. If the obstacle is a considerable distance from the takeoff point, the problem is essentially that of a long-term gain, and steady-state conditions will predominate. That is, acceleration from the takeoff speed to L/D max speed will be favorable because the maximum steady climb angle can be attained. However, if the obstacle is a relatively short distance from the takeoff point, the additional distance required to accelerate to L/D max speed may be detrimental, and the resulting situation may prove to be a short-term gain problem. In this case, it may prove necessary to begin climb out at or near the takeoff speed or hold the aircraft on the runway for extra speed and a subsequent zoom. The problem is sufficiently varied that no general conclusion can be applied to all jet aircraft, and particular procedures are specified for each aircraft in the flight handbook. Of greater general interest in climb performance are the factors which affect the rate of climb. The vertical velocity of an airplane depends on the flight speed and the inclination of the flight path. In fact, the rate of climb is the vertical component of the flight path velocity. By the diagram of Figure 2.21, the following relationship is developed. RC equals 101.3 times V times sine lowercase gamma, since sine gamma equals T minus D over W, then RC equals 101.3 times V times the quantity T minus D over W, and, with PA, equals TV over 325, and PR equals DV over 325, and RC equals 33,000 times PA minus PR over W. Where RC equals rate of climb in feet per minute, PA equals power available in horsepower, PR equals power required in horsepower, W equals weight in pounds, and V equals true airspeed in knots. The above relationship states that, for a given weight airplane, the rate of climb, RC, depends on the difference between the power available and the power required, PA minus PR, or excess power. Of course, when the excess power is 0, PA minus PR equals 0 or PA equals PR, the rate of climb is 0, and the airplane is in steady level flight. When the power available is greater than the power required, the excess power will allow a rate of climb specific to the magnitude of excess power. Also, when the power available is less than the power required, the deficiency of power produces a rate of descent. This relationship provides the basis for an important axiom of flight technique. For the conditions of steady flight, the power setting is the primary control of rate of climb or descent. One of the most important items of climb performance is the maximum rate of climb. By the previous equation for rate of climb, maximum rate of climb would occur where there exists the greatest difference between power available and power required, i.e., maximum, PA minus PR. Figure 2.21 illustrates the climb rate performance with the curves of power available and power required versus velocity. The power required curve is again a representative airplane which could be powered by either a turbojet or propeller-type powerplant. The power available curves included are for a characteristic propeller powerplant and jet powerplant operating at maximum output. The power curves for the representative propeller aircraft show a variation of propulsive power typical of a reciprocating engine-propeller combination. The maximum rate of climb for this aircraft will occur at some speed near the speed for L/D max. There is no direct relationship which establishes this situation, since the variation of propeller efficiency is the principal factor accounting for the variation of power available with velocity. In an ideal sense, if the propeller efficiency were constant, maximum rate of climb would occur at the speed for minimum power required. However, in the actual case, the propeller efficiency of the ordinary airplane will produce lower power available at low velocity and cause the maximum rate of climb to occur at a speed greater than that for minimum power required. The power curves for the representative jet aircraft show the near linear variation of power available with velocity. The maximum rate of climb for the typical jet airplane will occur at some speed much higher than that for maximum rate of climb of the equivalent propeller-powered airplane. In part, this is accounted for by the continued increase in power available with speed. Note that a 50% increase in thrust by use of an afterburner may cause an increase in rate of climb of approximately 100%. The climb performance of an airplane is affected by many various factors. The conditions of maximum climb angle or climb rate occur at specific speeds, and variations in speed will produce variations in climb performance. Generally, there is sufficient latitude that small variations in speed from the optimum do not produce large changes in climb performance, and certain operational items may require speeds slightly different from the optimum. Of course, climb performance would be most critical at high weight, high altitude, or during malfunction of a power plant. Then, optimum climb speeds are necessary. A change in airplane weight produces a twofold effect on climb performance. First, the weight, W, appears directly in denominator of the equations for both climb angle and climb rate. In addition, a change in weight will alter the drag and power required. Generally, an increase in weight will reduce the maximum rate of climb, but the airplane must be operated at some increase of speed to achieve the smaller peak climb rate, unless the airplane is compressibility limited. The effect of altitude on climb performance is illustrated by the composite graphs of Figure 2.22. Generally, an increase in altitude will increase the power required and decrease the power available. Hence, the climb performance of an airplane is expected to be greatly affected by altitude. The composite chart of climb performance depicts the variation with altitude of the speeds for maximum rate of climb, maximum angle of climb, and maximum and minimum level flight air speeds. As altitude is increased, these various speeds finally converge at the absolute ceiling of the airplane. At the absolute ceiling, there is no excess of power or thrust, and only one speed will allow steady level flight. The variation of rate of climb and maximum level flight speed with altitude for the typical propeller-powered airplane give evidence of the effect of supercharging. Distinct aberrations in these curves take place at the supercharger critical altitudes and blower shift points. The curve of time to climb is the result of summing up the increments of time spent climbing through increments of altitude. Note that approach to the absolute ceiling produces tremendous increase in the time curve. Specific reference points are established by these composite curves of climb performance. Of course, the absolute ceiling of the airplane produces zero rate of climb. The service ceiling is specified as the altitude which produces a rate of climb of 100 feet per minute. The altitude which produces a rate of climb of 500 feet per minute is termed the combat ceiling. Usually, these specific reference points are provided for the airplane at the combat configuration or a specific design configuration. The composite curves of climb performance for the typical turbojet airplane are shown in Figure 2.22. One particular point to note is the more rapid decay of climb performance with altitude above the tropopause. This is due in great part to the more rapid decay of engine thrust in the stratosphere. During a power-off descent, the deficiency of thrust and power define the angle of descent and rate of descent. Two particular points are of interest during a power-off descent: minimum angle of descent and minimum rate of descent. The minimum angle of descent would provide maximum glide distance through the air. Since no thrust is available from the power plant, minimum angle of descent would be obtained at L/D max. At L/D max, the deficiency of thrust is a minimum and, as shown by Figure 2.22, the greatest proportion between velocity and power required is obtained. The minimum rate of descent in power-off flight is obtained at the angle of attack and airspeed which produce minimum power required. For airplanes of moderate aspect ratio, the speed for minimum rate of descent is approximately 75% of the speed for minimum angle of descent. Range performance. The ability of an airplane to convert fuel energy into flying distance is one of the most important items of airplane performance. The problem of efficient range operation of an airplane appears of two general forms in flying operations. 1. To extract the maximum flying distance from a given fuel load, or 2. To fly a specified distance with minimum expenditure of fuel. An obvious common denominator for each of these operating problems is the specific range, nautical miles of flying distance per pound of fuel. Cruise flight for maximum range conditions should be conducted so that the airplane obtains maximum specific range throughout the flight. General range. The principal items of range performance can be visualized by use of the illustrations of Figure 2.23. From the characteristics of the aerodynamic configuration and the power plant, the conditions of steady level flight will define various rates of fuel flow throughout the range of flight speed. The first graph of Figure 2.23 illustrates a typical variation of fuel flow versus velocity. The specific range can be defined by the following relationship. Specific range equals nautical miles over pounds of fuel, or specific range equals nautical miles per hour over pounds of fuel per hour. Thus, specific range equals velocity in knots over fuel flow in pounds per hour. If maximum specific range is desired, the flight condition must provide a maximum of velocity fuel flow. This particular point would be located by drawing a straight line from the origin tangent to the curve of fuel flow versus velocity. The general item of range must be clearly distinguished from the item of endurance. The item of range involves consideration of flying distance, while endurance involves consideration of flying time. Thus, it is appropriate to define a separate term, specific endurance. Specific endurance equals flight hours over pounds of fuel. Specific endurance equals the quantity flight hours divided by hours over the quantity pounds of fuel divided by hours, in other words, pounds per hour. Then, specific endurance equals 1 over fuel flow in pounds per hour. By this definition, the specific endurance is simply the reciprocal of the fuel flow. Thus, if maximum endurance is desired, the flight condition must provide a minimum of fuel flow. This point is readily appreciated as the lowest point of the curve of fuel flow versus velocity. Generally, in subsonic performance, the speed at which maximum endurance is obtained is approximately 75% of the speed for maximum range. A more exact analysis of range may be obtained by a plot of specific range versus velocity, similar to the second graph of Figure 2.23. Of course, the source of these values of specific range is derived by the proportion of velocity and fuel flow from the previous curve of fuel flow versus velocity. The maximum specific range of the airplane is at the very peak of the curve. The maximum endurance point is located by a straight line from the origin tangent to the curve of specific range versus velocity. This tangency point defines a maximum of nautical miles per pound, per nautical miles per hour, or simply a maximum of hours per pound. While the very peak value of specific range would provide maximum range operation, long-range cruise operation is generally recommended at some slightly higher airspeed. Most long-range cruise operation is conducted at the flight condition which provides 99% of the absolute maximum specific range. The advantage of such operation is that 1% of range is traded for 3 to 5% higher cruise velocity. Since the higher cruise speed has a great number of advantages, the small sacrifice of range is a fair bargain. The curves of specific range versus velocity are affected by three principal variables: airplane gross weight, altitude, and the external aerodynamic configuration of the airplane. These curves are the source of range and endurance operating data, and are included in the performance section of the flight handbook. Cruise control of an airplane implies that the airplane is operated to maintain the recommended long-range cruise condition throughout the flight. Since fuel is consumed during cruise, the gross weight of the airplane will vary, and optimum airspeed, altitude, and power setting can vary. Generally, cruise control means the control of optimum airspeed, altitude, and power setting to maintain the 99% maximum specific range condition. At the beginning of cruise, the high initial weight of the airplane will require specific values of airspeed, altitude, and power setting to produce the recommended cruise condition. As fuel is consumed, and the airplane gross weight decreases, the optimum airspeed and power setting may decrease, or the optimum altitude may increase. Also, the optimum specific range will increase. The pilot must provide the proper cruise control technique to ensure that the optimum conditions are maintained. The final graph of figure 2.23 shows a typical variation of specific range with gross weight for some particular cruise operation. At the beginning of cruise, the gross weight is high, and the specific range is low. As fuel is consumed, and the gross weight reduces, the specific range increases. This type of curve relates the range obtained by the expenditure of fuel by the crosshatched area between the gross weights at beginning and end of cruise. For example, if the airplane begins cruise at 18,500 pounds and ends cruise at 13,000 pounds, 5,500 pounds of fuel is expended. If the average specific range were 0.2 nautical miles per pound, the total range would be range equals 0.2 nautical miles per pound times 5,500 pounds equals 1,100 nautical miles. Thus, the total range is dependent on both the fuel available and the specific range. When range and economy of operation predominate, the pilot must ensure that the airplane will be operated at the recommended long-range cruise condition. By this procedure, the airplane will be capable of its maximum design operating radius, or flight distances less than the maximum can be achieved with a maximum of fuel reserve at the destination. Range, propeller-driven airplanes. The propeller-driven airplane combines the propeller with the reciprocating engine or the gas turbine for propulsive power. In the case of either the reciprocating engine or the gas turbine combination, power plant fuel flow is determined mainly by the shaft power put into the propeller rather than thrust. Thus, the power plant fuel flow could be related directly to power required to maintain the airplane in steady, level flight. This fact allows study of the range of the propeller-powered airplane by analysis of the curves of power required versus velocity. Figure 2.24 illustrates a typical curve of power required versus velocity which, for the propeller-powered airplane, would be analogous to the variation of fuel flow versus velocity. Maximum endurance condition would be obtained at the point of minimum power required, since this would require the lowest fuel flow to keep the airplane in steady, level flight. Maximum range condition would occur where the proportion between velocity and power required is greatest, and this point is located by a straight line from the origin tangent to the curve. The maximum range condition is obtained at maximum lift-to-drag ratio, and it is important to note that L/D max, for a given airplane configuration, occurs at a particular angle of attack and lift coefficient and is unaffected by weight or altitude, within compressibility limits. Since approximately 50% of the total drag at L/D max is induced drag, the propeller-powered airplane which is designed specifically for long range will have a strong preference for the high aspect ratio planform. The effect of the variation of airplane gross weight is illustrated by the second graph of figure 2.24. The flight condition of L/D max is achieved at one particular value of lift coefficient for a given airplane configuration. Hence, a variation of gross weight will alter the values of airspeed, power required, and specific range obtained at L/D max. If a given configuration of airplane is operated at constant altitude, and the lift coefficient for L/D max, the following relationships will apply. V sub 2 over V sub 1 equals the square root of W sub 2 over W sub 1. PR sub 2 over PR sub 1 equals the quantity W sub 2 over W sub 1 raised to 3 over 2. SR sub 2 over SR sub 1 equals W sub 1 over W sub 2. Where condition 1 applies to some known condition of velocity, power required, and specific range for L/D max at some basic weight, W sub 1. Condition 2 applies to some new values of velocity, power required, and specific range for L/D max at some different weight, W sub 2, and V equals velocity in knots, W equals gross weight in pounds, PR equals power required in horsepower, and SR equals specific range in nautical miles per pound. Thus, a 10% increase in gross weight would create a 5% increase in velocity, a 15% increase in power required, and a 9% decrease in specific range. When flight is maintained at the optimum conditions of L/D max, the variations of velocity and power required must be monitored by the pilot as part of the cruise control to maintain L/D max. When the airplane fuel weight is a small part of the gross weight, and the range is small, then cruise control procedure can be simplified to essentially a constant speed and power setting throughout cruise. However, the long-range airplane has a fuel weight which is a considerable part of the gross weight, and cruise control procedure must employ scheduled airspeed and power changes to maintain optimum range conditions. The effect of altitude on the range of the propeller-powered airplane may be appreciated by inspection of the final graph of Figure 2.24. If a given configuration of airplane is operated at constant gross weight and the lift coefficient for L/D max, a change in altitude will produce the following relationships. V sub 2 over V sub 1 equals the square root of lowercase sigma sub 1 over lowercase sigma sub 2. PR sub 2 over PR sub 1 equals the square root of lowercase sigma sub 1 over lowercase sigma sub 2. Where condition 1 applies to some known condition of velocity and power required for L/D max at some original, basic altitude. Condition 2 applies to some new values of velocity and power required for L/D max at some different altitude, and V equals velocity in knots true airspeed, PR equals power required in horsepower, and lowercase sigma equals altitude density ratio. Thus, if flight is conducted at 22,000 feet, lowercase sigma equals 0.498, the airplane will have a 42% higher velocity and a 42% higher power required than when operating at sea level. Of course, the greater velocity is a higher TAS, since the airplane at a given weight and lift coefficient will require the same PAS independent of altitude. Also, the drag of the airplane at altitude is the same as the drag at sea level, but the higher TAS causes a proportionately greater power required. Note that the same straight line from the origin tangent to the sea level power curve also is tangent to the altitude power curve. The effect of altitude on specific range can be appreciated from the previous relationships. If a change in altitude causes identical changes in velocity and power required, the proportion of velocity to power required would be unchanged. This fact implies that the specific range of the propeller-powered airplane would be unaffected by altitude. In the actual case, this is true to the extent that powerplant-specific fuel consumption, lowercase c, and propeller efficiency, lowercase eta sub p, are the principal factors which could cause a variation of specific range with altitude. If compressibility effects are negligible, any variation of specific range with altitude is strictly a function of engine propeller performance. The airplane equipped with the reciprocating engine will experience very little, if any, variation of specific range with altitude at low altitudes. There is negligible variation of brake-specific fuel consumption for values of bhp below the maximum cruise power rating of the power plant, which is the auto-lean or manual lean range of engine operation. Thus, an increase in altitude will produce a decrease in specific range only when the increased power requirement exceeds the maximum cruise power rating of the power plants. One advantage of supercharging is that the cruise power may be maintained at high altitude, and the airplane may achieve the range at high altitude with the corresponding increase in TAS. The principal differences in the high-altitude cruise and low-altitude cruise are the true airspeeds and climb fuel requirements. The airplane equipped with the turboprop power plant will exhibit a variation of specific range with altitude for two reasons. First, the specific fuel consumption, lowercase c, of the turbine engine improves with the lower inlet temperatures common to high altitudes. Also, the low power requirements to achieve optimum aerodynamic conditions at low altitude necessitate engine operation at low, inefficient output power. The increased power requirements at high altitudes allow the turbine power plant to operate in an efficient output range. Thus, while the airplane has no particular preference for altitude, the power plants prefer the higher altitudes and cause an increase in specific range with altitude. Generally, the upper limit of altitude for efficient cruise operation is defined by airplane gross weight and power required, or compressibility effects. The optimum climb and descent for the propeller-powered airplane is affected by many different factors and no general, all-inclusive relationship is applicable. Handbook data for the specific airplane and various operational factors will define operating procedures. Range, turbojet airplanes. Many different factors influence the range of the turbojet airplane. In order to simplify the analysis of the overall range problem, it is convenient to separate airplane factors from powerplant factors and analyze each item independently. An analogy would be the study of horse cart performance by separating cart performance from horse performance to distinguish the principal factors which affect the overall performance. In the case of the turbojet airplane, the fuel flow is determined mainly by the thrust rather than power. Thus, the fuel flow could be most directly related to the thrust required to maintain the airplane in steady, level flight. This fact allows study of the turbojet-powered airplane by analysis of the curves of thrust required versus velocity. Figure 2.25 illustrates a typical curve of thrust required versus velocity, which would be somewhat analogous to the variation of fuel flow versus velocity. Maximum endurance condition would be obtained at L/D max, since this would incur the lowest fuel flow to keep the airplane in steady, level flight. Maximum range condition would occur where the proportion between velocity and thrust required is greatest, and this point is located by a straight line from the origin tangent to the curve. The maximum range is obtained at the aerodynamic condition, which produces a maximum proportion between the square root of the lift coefficient, CL, and the drag coefficient, CD, or the square root of CL/CD max. In subsonic performance, the square root of CL/CD max occurs at a particular value of angle of attack and lift coefficient and is unaffected by weight or altitude, within compressibility limits. At this specific aerodynamic condition, induced drag is approximately 25% of the total drag, so the turbojet airplane designed for long range does not have the strong preference for high aspect ratio planform like the propeller airplane. On the other hand, since approximately 75% of the total drag is parasite drag, the turbojet airplane designed specifically for long range has the special requirement for great aerodynamic cleanness. The effect of the variation of airplane gross weight is illustrated by the second graph of figure 2.25. The flight condition of the square root of CL/CD max is achieved at one value of lift coefficient for a given airplane in subsonic flight. Hence, a variation of gross weight will alter the values of airspeed, thrust required, and specific range obtained at the square root of CL/CD max. If a given configuration is operated at constant altitude and lift coefficient, the following relationships will apply. V sub 2 over V sub 1 equals the square root of W sub 2 over W sub 1. TR sub 2 over TR sub 1 equals W sub 2 over W sub 1. SR sub 2 over SR sub 1 equals the square root of W sub 1 over W sub 2, constant altitude. Where condition 1 applies to some known condition of velocity, thrust required, and specific range for the square root of CL/CD max at some basic weight, W sub 1. Condition 2 applies to some new values of velocity, thrust required, and specific range for the square root of CL/CD max at some basic weight, W sub 2. And V equals velocity in knots, W equals gross weight in pounds. TR equals thrust required in pounds, and SR equals specific range in nautical miles per pound. Thus, a 10% increase in gross weight would create a 5% increase in velocity, a 10% increase in thrust required, and a 5% decrease in specific range when flight is maintained at the optimum conditions of the square root of CL/CD max. Since most jet airplanes have a fuel weight which is a large part of the gross weight, cruise control procedures will be necessary to account for the changes in optimum airspeeds and power settings as fuel is consumed. The effect of altitude on the range of the turbojet airplane is of great importance because no other single item can cause such large variations of specific range. If a given configuration of airplane is operated at constant gross weight, and the lift coefficient for the square root of CL/CD max, a change in altitude will produce the following relationships. V sub 2 over V sub 1 equals the square root of lowercase sigma sub 1 over lowercase sigma sub 2. TR equals a constant, neglecting compressibility effects. SR sub 2 over SR sub 1 equals the square root of lowercase sigma sub 1 over lowercase sigma sub 2. Where condition 1 applies to some known condition of velocity, thrust required, and specific range for the square root of CL/CD max at some original, basic altitude. Condition 2 applies to some new values of velocity, thrust required, and specific range for the square root of CL/CD max at some different altitude. And V equals velocity in knots true airspeed, TR equals thrust required in pounds, SR equals specific range in nautical miles per pound, and lowercase sigma equals altitude density ratio. Thus, if flight is conducted at 40,000 feet, lowercase sigma equals 0.246, the airplane will have a 102% higher velocity, the same thrust required, and a 102% higher specific range, even when the beneficial effects of altitude on engine performance are neglected, than when operating at sea level. Of course, the greater velocity is a higher TAS, and the same thrust required must be obtained with a greater engine RPM. At this point, it is necessary to consider the effect of the operating condition on power plant performance. An increase in altitude will improve power plant performance in two respects. First, an increase in altitude when below the tropopause will provide lower inlet air temperatures, which reduce the specific fuel consumption, lowercase c sub t. Of course, above the tropopause, the specific fuel consumption tends to increase. At low altitude, the engine RPM necessary to produce the required thrust is low and, generally, well below the normal rated value. Thus, a second benefit of altitude on engine performance is due to the increased RPM required to furnish cruise thrust. An increase in engine speed to the normal rated value will reduce the specific fuel consumption. The increase in specific range with altitude of the turbojet airplane can be attributed to these three factors. 1. An increase in altitude will increase the proportion of V over TR and provide a greater TAS for the same TR. 2. An increase in altitude in the troposphere will produce lower inlet air temperature, which reduces the specific fuel consumption. 3. An increase in altitude requires increased engine RPM to provide cruise thrust, and the specific fuel consumption reduces as normal rated RPM is approached. The combined effect of these three factors defines altitude as the one most important item affecting the specific range of the turbojet airplane. As an example of this combined effect, the typical turbojet airplane obtains a specific range at 40,000 feet, which is approximately 150% greater than that obtained at sea level. The increased TAS accounts for approximately 2/3 of this benefit, while increased engine performance, reduced lowercase cl, accounts for the other 1/3 of the benefit. For example, at sea level, the maximum specific range of a turbojet airplane may be 0.1 nautical miles per pound, but at 40,000 feet, the maximum specific range would be approximately 0.25 nautical miles per pound. From the previous analysis, it is apparent that the cruise altitude of the turbojet should be as high as possible within compressibility or thrust limits. Generally, the optimum altitude to begin cruise is the highest altitude at which the maximum continuous thrust can provide the optimum aerodynamic conditions. Of course, the optimum altitude is determined mainly by the gross weight at the beginning of cruise. For the majority of turbojet airplanes, this altitude will be at or above the tropopause for normal cruise configurations. Most turbojet airplanes which have transonic or moderate supersonic performance will obtain maximum range with a high subsonic cruise. However, the airplane designed specifically for high supersonic performance will obtain maximum range with a supersonic cruise, and subsonic operation will cause low lift-to-drag ratios, poor inlet and engine performance, and reduce the range capability. The cruise control of the turbojet airplane is considerably different from that of the propeller-driven airplane. Since the specific range is so greatly affected by altitude, the optimum altitude for the beginning of cruise should be attained as rapidly as is consistent with climb fuel requirements. The range climb program varies considerably between airplanes, and the performance section of the flight handbook will specify the appropriate procedure. The descent from cruise altitude will employ essentially the same feature. A rapid descent is necessary to minimize the time at low altitudes where specific range is low and fuel flow is high for a given engine speed. During cruise flight of the turbojet airplane, the decrease of gross weight from expenditure of fuel can result in two types of cruise control. During a constant altitude cruise, a reduction in gross weight will require a reduction of airspeed and engine thrust to maintain the optimum lift coefficient of subsonic cruise. While such a cruise may be necessary to conform to the flow of traffic, it constitutes a certain inefficiency of operation. If the airplane were not restrained to a particular altitude, maintaining the same lift coefficient and engine speed would allow the airplane to climb as the gross weight decreases. Since altitude generally produces a beneficial effect on range, the climbing cruise implies a more efficient flight path. The cruising flight of the turbojet airplane will begin usually at or above the tropopause in order to provide optimum range conditions. If flight is conducted at the square root of CL over CD max, optimum range will be obtained at specific values of lift coefficient and drag coefficient. When the airplane is fixed at these values of CL and CD, and the TAS is held constant, both lift and drag are directly proportional to the density ratio, lowercase sigma. Also, above the tropopause, the thrust is proportional to lowercase sigma when the TAS and RPM are constant. As a result, a reduction of gross weight by the expenditure of fuel would allow the airplane to climb, but the airplane would remain in equilibrium because lift, drag, and thrust all vary in the same fashion. This relationship is illustrated by Figure 2.26. The relationship of lift, drag, and thrust is convenient, for, in part, it justifies the condition of a constant velocity. Above the tropopause, the speed of sound is constant. Hence, a constant velocity during the cruise climb would produce a constant Mach number. In this case, the optimum values of the square root of CL over CD max, CL, and CD do not vary during the climb, since the Mach number is constant. The specific fuel consumption is initially constant above the tropopause, but begins to increase at altitudes much above the tropopause. If the specific fuel consumption is assumed to be constant during the cruise climb, the following relationships will apply. V, M, CL, and CD are constant. Lowercase sigma sub 2 over lowercase sigma sub 1 equals W sub 2 over W sub 1. Fuel flow sub 2 over fuel flow sub 1 equals lowercase sigma sub 2 over lowercase sigma sub 1. SR sub 2 over SR sub 1 equals W sub 1 over W sub 2. Cruise climb above tropopause, constant M, constant lowercase c sub t. Where condition 1 applies to some known condition of weight, fuel flow, and specific range at some original basic altitude during cruise climb. Condition 2 applies to some new values of weight, fuel flow, and specific range at some different altitude along a particular cruise path. And V equals velocity in knots, M equals Mach number, W equals gross weight in pounds, fuel flow equals fuel flow in pounds per hour, SR equals specific range in nautical miles per pound, and lowercase sigma equals altitude density ratio. Thus, during a cruise climb flight, a 10% decrease in gross weight from the consumption of fuel would create no change in Mach number or TAS, a 5% decrease in EAS, a 10% decrease in lowercase sigma, i.e., higher altitude, a 10% decrease in fuel flow, and an 11% increase in specific range. An important comparison can be made between the constant altitude cruise and the cruise climb with respect to the variation of specific range. From the previous relationships, a 2% reduction in gross weight during cruise would create a 1% increase in specific range in a constant altitude cruise, but a 2% increase in specific range in a cruise climb at constant Mach number. SR sub 2 over SR sub 1 equals the square root of W sub 1 over W sub 2, constant altitude. SR sub 2 over SR sub 1 equals W sub 1 over W sub 2, cruise climb. Thus, a higher average specific range can be maintained during the expenditure of a given increment of fuel. If an airplane begins a cruise at optimum conditions at or above the tropopause with a given weight of fuel, the included data provide a comparison of the total range available from a constant altitude or cruise climb flight path. For example, if the cruise fuel weight is 50% of the gross weight, the climbing cruise flight path will provide a range 18.2% greater than cruise at constant altitude. This comparison does not include consideration of any variation of specific fuel consumption during cruise or the effects of compressibility in defining the optimum aerodynamic conditions for cruising flight. However, the comparison is generally applicable for aircraft which have subsonic cruise. When the airplane has a supersonic cruise for maximum range, the optimum flight path is generally one of a constant Mach number. The optimum flight path is generally but not necessarily a climbing cruise. In this case of subsonic or supersonic cruise, a Mach meter is of principal importance in cruise control of the jet airplane. The effect of wind on range is of considerable importance in flying operations. Of course, a headwind will always reduce range, and a tailwind will always increase range. The selection of a cruise altitude with the most favorable, or least unfavorable, winds is a relatively simple matter for the case of the propeller-powered airplane. Since the range of the propeller-powered airplane is relatively unaffected by altitude, the altitude with the most favorable winds is selected for range. However, the range of the turbojet airplane is greatly affected by altitude, so the selection of an optimum altitude will involve considering the wind profile with the variation of range with altitude. Since the turbojet range increases greatly with altitude, the turbojet can tolerate less favorable, or more unfavorable, winds with increased altitude. In some cases, large values of wind may cause a significant change in cruise velocity to maintain maximum ground nautical miles per pound of fuel. As an example of an extreme condition, consider an airplane flying into a headwind which equals the cruise velocity. In this case, any increase in velocity would improve range. To appreciate the changes in optimum speeds with various winds, refer to the illustration of Figure 2.26. When zero wind conditions exist, a straight line from the origin tangent to the curve of fuel flow versus velocity will locate maximum range conditions. When a headwind condition exists, the speed for maximum ground range is located by a line tangent drawn from a velocity offset equal to the headwind velocity. This will locate maximum range at some higher velocity and fuel flow. Of course, the range will be less than when at zero wind conditions, but the higher velocity and fuel flow will minimize the range loss due to the headwind. In a similar sense, a tailwind will reduce the cruise velocity to maximize the benefit of the tailwind. The procedure of employing different cruise velocities to account for the effects of wind is necessary only at extreme values of wind velocity. It is necessary to consider the change in optimum cruise airspeed when the wind velocities exceed 25% of the zero wind cruise velocity. Endurance performance. The ability of the airplane to convert fuel energy into flying time is an important factor in flying operations. The specific endurance of the airplane is defined as follows. Specific endurance equals flight hours over pounds of fuel, or specific endurance equals 1 over fuel flow in pounds per hour. The specific endurance is simply the reciprocal of the fuel flow, hence, maximum endurance conditions would be obtained at the lowest fuel flow required to hold the airplane in steady level flight. Obviously, minimum fuel flow will provide the maximum flying time from a given quantity of fuel. Generally, in subsonic performance, the speed at which maximum endurance is achieved is approximately 75% of the speed for maximum range. While many different factors can affect the specific endurance, the most important factors at the control of the pilot are the configuration and operating altitude. Of course, for maximum endurance conditions, the airplane must be in the clean configuration and operated at the proper aerodynamic conditions. Effect of altitude on endurance, propeller-driven airplanes. Since the fuel flow of the propeller-driven airplane is proportional to power required, the propeller-powered airplane will achieve maximum specific endurance when operated at minimum power required. The point of minimum power required is obtained at a specific value of lift coefficient for a particular airplane configuration and is essentially independent of weight or altitude. However, an increase in altitude will increase the value of the minimum power required as illustrated by Figure 2.27. If the specific fuel consumption were not influenced by altitude or engine power, the specific endurance would be directly proportional to the square root of sigma, e.g., the specific endurance at 22,000 feet, lowercase sigma, equals 0.498, would be approximately 70% of the value at sea level. This example is very nearly the case of the airplane with the reciprocating engine, since specific fuel consumption and propeller efficiency are not directly affected by altitude. The obvious conclusion is that maximum endurance of the reciprocating engine airplane is obtained at the lowest practical altitude. The variation with altitude of the maximum endurance of the turboprop airplane requires consideration of powerplant factors in addition to airplane factors. The turboprop powerplant prefers operation at low inlet air temperatures and relatively high power setting to produce low specific fuel consumption. While an increase in altitude will increase the minimum power required for the airplane, the power plant achieves more efficient operation. As a result of these differences, maximum endurance of the multi-engine turboprop airplane at low altitudes may require shutting down some of the power plants in order to operate the remaining power plants at a higher, more efficient power setting. Effect of altitude on endurance, turbojet airplanes. Since the fuel flow of the turbojet-powered airplane is proportional to thrust required, the turbojet airplane will achieve maximum specific endurance when operated at minimum thrust required, or L/D max. In subsonic flight, L/D max occurs at a specific value of lift coefficient for a given airplane and is essentially independent of weight or altitude. If a given weight and configuration of airplane is operated at various altitudes, the value of the minimum thrust required is unaffected by the curves of thrust required versus velocity shown in Figure 2.27. Hence, it is apparent that the aerodynamic configuration has no preference for altitude, within compressibility limits, and specific endurance is a function only of engine performance. The specific fuel consumption of the turbojet engine is strongly affected by operating RPM and altitude. Generally, the turbojet engine prefers the operating range near normal rated engine speed and the low temperatures of the stratosphere to produce low specific fuel consumption. Thus, increased altitude provides the favorable lower inlet air temperature and requires a greater engine speed to provide the thrust required at L/D max. The typical turbojet airplane experiences an increase in specific endurance with altitude, with the peak values occurring at or near the tropopause. For example, a typical single-engine turbojet airplane will have a maximum specific endurance at 35,000 feet, which is at least 40% greater than the maximum value at sea level. If the turbojet airplane is at low altitude, and it is necessary to hold for a considerable time, maximum time in the air will be obtained by beginning a climb to some optimum altitude dependent upon the fuel quantity available. Even though fuel is expended during the climb, the higher altitude will provide greater total endurance. Of course, the use of afterburner for the climb would produce a prohibitive reduction in endurance. Off-optimum range and endurance. There are many conditions of flying operations in which optimum range or endurance conditions are not possible or practical. In many instances, the off-optimum conditions result from certain operational requirements or simplification of operating procedures. In addition, off-optimum performance may be the result of a power plant malfunction or failure. The most important conditions are discussed for various airplanes by power plant type. Reciprocating powered airplane. In the majority of cases, the reciprocating powered airplane is operated at an engine-dictated cruise. Service use will most probably define some continuous power setting which will give good service life and trouble-free operation of the power plant. When range or endurance is of no special interest, the simple expedient is to operate the power plant at the recommended power setting and accept whatever speed, range, or endurance that results. While such a procedure greatly simplifies the matter of cruise control, the practice does not provide the necessary knowledge required for operating a high-performance, long-range airplane. The failure of an engine on the multi-engine reciprocating powered airplane has interesting ramifications. The first problem is to produce sufficient power from the remaining engines to keep the airplane airborne. The problem will be most critical if the airplane is at high altitude, high gross weight, and with flaps and gear extended. Lower altitude, jettisoning of weight items, and cleaning up the airplane will reduce the power required for flight. Of course, the propeller on the inoperative engine must be feathered, or the power required may exceed that available from the remaining operating power plants. The effect on range is much dependent on the airplane configuration. When the propeller on the inoperative engine is feathered, the added drag is at a minimum, but there is added trim drag required to balance the unsymmetrical power. When both these sources of added drag are accounted for, the L/D max is reduced, but not by significant amounts. Generally, if the specific fuel consumption and propeller efficiency do not deteriorate, the maximum specific range is not greatly reduced. On the twin-engine airplane, the power required must be furnished by the one remaining engine, and this usually requires more than the maximum cruise rating of the power plant. As a result, the power plant cannot be operated in the auto-lean or manual lean power range, and the specific fuel consumption increases greatly. Thus, noticeable loss of range must be anticipated when one engine fails on the twin-engine airplane. The failure of one engine on the 4 or more engine airplane may allow the required power to be developed by the 3 remaining power plants operating in an economical power range. If the airplane is clean, at low altitude, and low gross weight, the failure of one engine is not likely to cause a loss of range. However, the loss of two engines is likely to cause a considerable loss of range. When engine failure produces a critical power or range situation, improved performance is possible with the airplane in the clean configuration at low altitude. Also, jettisoning of expendable weight items will reduce the power required and improve the specific range. Turboprop-powered airplane. The turbine engine has the preference for relatively high power settings and high altitudes to provide low specific fuel consumption. Thus, the off-optimum conditions of range or endurance can be concerned with altitudes less than the optimum. Altitudes less than the optimum can reduce the range, but the loss can be minimized on the multi-engine airplane by shutting down some power plants and operating the remaining power plants at a higher, more efficient output. In this case, the change of range is confined to the variation of specific fuel consumption with altitude. Essentially, the same situation exists in the case of engine failure when cruising at optimum altitude. If the propeller on the inoperative engine is feathered, the loss of range will be confined to the change in specific fuel consumption from the reduced cruise altitude. If a critical power situation exists due to engine failure, a reduction in altitude provides immediate benefit because of the reduction of power required and the increase in power available from the power plants. In addition, the jettisoning of expendable weight items will improve performance and, of course, the clean configuration provides minimum parasite drag. Maximum specific endurance of the turboprop airplane does not vary as greatly with altitude as the turbojet airplane. While each configuration has its own particular operating requirements, low-altitude endurance of the turboprop airplane requires special consideration. The single-engine turboprop will generally experience an increase in specific endurance with an increase in altitude from sea level. However, if the airplane is at low altitude and must hold or endure for a period of time, the decision to begin a climb or hold the existing altitude will depend on the quantity of fuel available. The decision depends primarily on the climb fuel requirements and the variation of specific endurance with altitude. A somewhat similar problem exists with the multi-engine turboprop airplane, but additional factors are available to influence the specific endurance at low altitude. In other words, low-altitude endurance can be improved by shutting down some power plants and operating the remaining power plants at a higher, more efficient power setting. Many operational factors could decide whether such procedure would be a suitable technique. Turbojet-powered airplane. Increasing altitude has a powerful effect on both the range and endurance of the turbojet airplane. As a result of this powerful effect, the typical turbojet airplane will achieve maximum specific endurance at or near the tropopause. Also, the maximum specific range will be obtained at even higher altitudes, since the peak specific range generally occurs at the highest altitude at which the normal rating of the engine can sustain the optimum aerodynamic conditions. At low-altitude cruise conditions, the engine speed necessary to sustain optimum aerodynamic conditions is very low, and the specific fuel consumption is relatively poor. Thus, at low altitude, the airplane prefers the low speeds to obtain the square root of capital CL over CD max, but the power plant prefers the higher speeds common to higher engine efficiency. The compromise results in maximum specific range at flight speeds well above the optimum aerodynamic conditions. In a sense, low-altitude cruise conditions are engine-dictated. Altitude is the one most important factor affecting the specific range of the turbojet airplane. Any operation below the optimum altitude will have a noticeable effect on the range capability, and proper consideration must be given to the loss of range. In addition, turbojet airplanes designed specifically for long range will have a large percent of the gross weight as fuel. The large changes in gross weight during cruise will require particular methods of cruise control to extract the maximum flight range. A variation from the optimum flight path of cruise, that is, constant Mach number, cruise climb, or whatever the appropriate technique, will result in a loss of range capability. The failure of an engine during the optimum cruise of a multi-engine turbojet airplane will cause a noticeable loss of range. Since the optimum cruise of the turbojet is generally a thrust-limited cruise, the loss of part of the total thrust means that the airplane must descend to a lower altitude. For example, if a twin-engine jet begins an optimum cruise at 35,000 feet, lowercase sigma, equals 0.31, and one power plant fails, the airplane must descend to a lower altitude so that the operative engine can provide the cruise thrust. The resulting altitude would be approximately 16,000 feet, lowercase sigma, equals 0.61. Thus, the airplane will experience a loss of the range remaining at the point of engine failure, and loss could be accounted for by the reduced velocity, TAS, and the increase in specific fuel consumption, lowercase c sub t, from the higher ambient air temperature. In the case of the example airplane, engine failure would cause a 30 to 40% loss of range from the point of engine failure. Of course, the jettisoning of expendable weight items would allow higher altitude and would increase the specific range. Maximum endurance in the turbojet airplane varies with altitude, but the variation is due to the changes in fuel flow necessary to provide the thrust required at L/D max. The low inlet air temperature of the tropopause, and the greater engine speed, reduce the specific fuel consumption to a minimum. If the single-engine turbojet airplane is at low altitude and must hold or endure for a period of time, a climb should begin to take advantage of the higher specific endurance at higher altitude. The altitude to which to climb will be determined by the quantity of fuel remaining. In the case of the multi-engine turbojet at low altitude, some slightly different procedure may be utilized. If all power plants are operating, it is desirable to climb to a higher altitude, which is a function of the remaining fuel quantity. An alternative at low altitude would be to provide the endurance thrust with some engines shut down, and the remaining engines operating at a more efficient power output. This technique would cause a minimum loss of endurance if at low altitude. The feasibility of such a procedure is dependent on many operational factors. In all cases, the airplane should be in the cleanest possible external configuration because the specific endurance is directly proportional to the L/D. Maneuvering performance. When the airplane is in turning flight, the airplane is not in static equilibrium, for there must be developed the unbalance of force to produce the acceleration of the turn. During a steady coordinated turn, the lift is inclined to produce a horizontal component of force to equal the centrifugal force of the turn. In addition, the steady turn is achieved by producing a vertical component of lift which is equal to the weight of the airplane. Figure 2.28 illustrates the forces which act on the airplane in a steady, coordinated turn. For the case of the steady, coordinated turn, the vertical component of lift must equal the weight of the aircraft so that there will be no acceleration in the vertical direction. This requirement leads to the following relationship. Lowercase n equals L/W, or lowercase n equals 1 over cosine lowercase phi, or lowercase n equals secant phi, where n equals load factor or G, L equals lift in pounds, and lowercase phi equals bank angle in degrees. From this relationship, it is apparent that the steady, coordinated turn requires specific values of load factor, lowercase n, at various angles of bank, lowercase phi. For example, a bank angle of 60 degrees requires a load factor of 2.0, cosine 60 equals 0.5, or secant 60 equals 2.0, to provide the steady, coordinated turn. If the airplane were at a 60-degree bank and lift were not provided to produce the exact load factor of 2.0, the aircraft would be accelerating in the vertical direction as well as the horizontal direction, and the turn would not be steady. Also, any side force on the aircraft due to sideslip, etc., would place the resultant aerodynamic force out of the plane of symmetry perpendicular to the lateral axis, and the turn would not be coordinated. As a consequence of the increased lift required to produce the steady turn in a bank, the induced drag is increased above that incurred by steady, wing-level, lift-equal-weight flight. In a sense, the increased lift required in a steady turn will increase the total drag, or power required, in the same manner as increased gross weight in level flight. The curves of figure 2.28 illustrate the general effect of turning flight on the total thrust and power required. Of course, the change in thrust required at any given speed is due to the change in induced drag, and the magnitude of change depends on the value of induced drag in level flight, and the angle of bank in turning flight. Since the induced drag generally varies as the square of capital CL, the following data provide an illustration of the effect of various degrees of bank. Bank angle 0 degrees. Load factor 1.000 Gs. Percent increase in induced drag from level flight 0%. Bank angle 15 degrees. Load factor 1.036 Gs. Percent increase in induced drag from level flight 7.2%. Bank angle 30 degrees. Load factor 1.154 Gs. Percent increase in induced drag from level flight 33.3%. Bank angle 45 degrees. Load factor 1.414 Gs. Percent increase in induced drag from level flight 100%. Bank angle 60 degrees. Load factor 2.000 Gs. Percent increase in induced drag from level flight 300%. Since the induced drag predominates at low speeds, steep turns at low speeds can produce significant increases in thrust or power required to maintain altitude. Thus, steep turns must be avoided after takeoff, during approach, and especially during a critical power situation from failure or malfunction of a power plant. The greatly increased induced drag is just as important, if not more important, as the increased stall speed in turning flight. It is important also that any turn be well coordinated to prevent the increased drag attendant to a side slip. Turning performance. The horizontal component of lift will equal the centrifugal force of steady, turning flight. This fact allows development of the following relationships of turning performance. Turn radius. R equals V squared over 11.26 times tangent lowercase phi. Where R equals turn radius feet, V equals velocity in knots true airspeed, lowercase phi equals bank angle in degrees, turn rate. ROT equals 1091 times tangent lowercase phi over V. Where ROT equals rate of turn in degrees per second, lowercase phi equals bank angle in degrees, and V equals velocity in knots true airspeed. These relationships define the turn radius, R, and rate of turn, ROT, as functions of the two principal variables. Bank angle, lowercase phi, and velocity, V, in true airspeed. Thus, when the airplane is flown in the steady, coordinated turn at specific values of bank angle and velocity, the turn rate and turn radius are fixed and independent of the airplane type. As an example, an airplane in a steady, coordinated turn at a bank angle of 45 and a velocity of 250 knots true airspeed would have the following turn performance. R equals 250 squared over 11.26 times 1.000. Tangent 45 degrees equals 1.000. R equals 5,550 feet, and ROT equals 1091 times 1.000 over 250, ROT equals 4.37 degrees per second. If the airplane were to hold the same angle of bank at 500 knots true airspeed, the turn radius would quadruple, R equals 22,200 feet, and the turn rate would be one-half the original value, ROT equals 2.19 degrees per second. Values of turn radius and turn rate versus velocity are shown in figure 2.29 for various angles of bank, and the corresponding load factors. The conditions are for the steady, coordinated turn at constant altitude, but the results are applicable for climbing or descending flight when the angle of climb or descent is relatively small. While the effect of altitude on turning performance is not immediately apparent from these curves, the principal effect must be appreciated as an increased true airspeed for a given equivalent airspeed. Tactical. Many tactical maneuvers require the use of the maximum turning capability of the airplane. The maximum turning capability of an airplane will be defined by three factors. 1. Maximum lift capability. The combination of maximum lift coefficient, CL max, and wing loading, W/S, will define the ability of the airplane to develop aerodynamically the load factors of maneuvering flight. 2. Operating strength limits will define the upper limits of maneuvering load factors which will not damage the primary structure of the airplane. These limits must not be exceeded in normal operations because of the possibility of structural damage or failure. 3. Thrust or power limits will define the ability of the airplane to turn at constant altitude. The limiting condition would allow increased load factor and induced drag until the drag equals the maximum thrust available from the power plant. Such a case would produce the maximum turning capability for maintaining constant altitude. The first illustration of figure 2.30 shows how the aerodynamic and structural limits define the maximum turning performance. The aerodynamic limit describes the minimum turn radius available to the airplane when operated at CL max. When the airplane is at the stall speed in level flight, all the lift is necessary to sustain the aircraft in flight, and none is available to produce a steady turn. Hence, the turn radius at the stall speed is infinite. As speed is increased above the stall speed, the airplane at CL max is able to develop lift greater than weight and produce a finite turn radius. For example, at a speed twice the stall speed, the airplane at CL max is able to develop a load factor of 4 and utilize a bank angle of 75.5 degrees, cosine 75.5, equals 0.25. Continued increase in speed increases the load factor and bank angle which are available aerodynamically, but because of the increase in velocity, and the basic effect on turn radius, the turn radius approaches an absolute minimum value. When CL max is unaffected by velocity, the aerodynamic minimum turn radius approaches this absolute value, which is a function of CL max, W over S, and lowercase sigma. Actually, the one common denominator of aerodynamic turning performance is the wing level stall speed. The aerodynamic limit of turn radius requires that the increased velocity be utilized to produce increasing load factors and greater angles of bank. Obviously, very high speeds will require very high load factors, and the absolute aerodynamic minimum turn radius will require an infinite load factor. Increasing speed above the stall speed will eventually produce the limit load factor, and continued increase in speed above this point will require that load factor and bank angle be limited to prevent structural damage. When the load factor and bank angle are held constant at the structural limit, the turn radius varies as the square of the velocity, and increases rapidly above the aerodynamic limit. The intersection of the aerodynamic limit and structural limit lines is the maneuvering speed. The maneuvering speed is the minimum speed necessary to develop aerodynamically the limit load factor, and it produces the minimum turn radius within aerodynamic and structural limitations. At speeds less than the maneuvering speed, the limit load factor is not available aerodynamically, and turning performance is aerodynamically limited. At speeds greater than the maneuvering speed, CL max and maximum aerodynamic load factor are not available and turning performance is structurally limited. When the stall speed and limit load factor are known for a particular configuration, the maneuvering speed is related by the following expression. VA equals VS times the square root of lowercase n limit, where VA equals maneuvering speed in knots, VS equals stall speed in knots, and n limit equals limit load factor. For example, an airplane with a limit load factor of 4.0 would have a maneuvering speed which is twice the stall speed. The aerodynamic limit line of the first illustration of figure 2.30 is typical of an airplane with a CL max which is invariant with speed. While this is applicable for the majority of subsonic airplanes, considerable difference would be typical of the transonic or supersonic airplane at altitude. Compressibility effects and changes in longitudinal control power may produce a maximum available CL max, which varies with velocity, and an aerodynamic turn radius which is not an absolute minimum at the maximum of velocity. The second illustration of figure 2.30 describes the constant altitude turning performance of an airplane. When an airplane is at high altitude, the turning performance at the high speed end of the flight speed range is more usually thrust limited rather than structurally limited. In flight at constant altitude, the thrust must equal the drag to maintain equilibrium and, thus, the constant altitude turn radius is infinite at the maximum level flight speed. Any bank or turn at maximum level flight speed would incur additional drag and cause the airplane to descend. However, as speed is reduced below the maximum level flight speed, parasite drag reduces, and allows increased load factors and bank angles and reduced radius of turn, i.e., decreased parasite drag allows increased induced drag to accommodate turns within the maximum thrust available. Thus, the considerations of constant altitude will increase the minimum turn radius above the aerodynamic limit and define a particular airspeed for minimum turn radius. Each of the three limiting factors, aerodynamic, structural, and power, may combine to define the turning performance of an airplane. Generally, aerodynamic and structural limits predominate at low altitude, while aerodynamic and power limits predominate at high altitude. The knowledge of this turning performance is particularly necessary for effective operation of fighter and interceptor types of airplanes. Takeoff and landing. The majority of pilot-caused airplane accidents occur during the takeoff and landing phase of flight. Because of this fact, the naval aviator must be familiar with all the many variables which influence the takeoff and landing performance of an airplane, and must strive for exacting, professional techniques of operation during these phases of flight. Takeoff and landing performance are conditions of accelerated motion. For instance, during takeoff the airplane starts at zero velocity and accelerates to the takeoff velocity to become airborne. During landing, the airplane touches down at the landing speed and decelerates, or accelerates negatively, to the zero velocity of the stop. In fact, the landing performance could be considered as a takeoff in reverse for purposes of study. In either case, takeoff or landing, the airplane is accelerated between zero velocity and the takeoff or landing velocity. The important factors of takeoff or landing performance are: 1. The takeoff or landing velocity, which will generally be a function of the stall speed or minimum flying speed, e.g., 15% above the stall speed. 2. The acceleration during the takeoff or landing roll. The acceleration experienced by any object varies directly with the unbalance of force and inversely with the mass of the object. 3. The takeoff or landing roll distance is a function of both the acceleration and velocity. In the actual case, the takeoff and landing distance is related to velocity and acceleration in a very complex fashion. The main source of the complexity is that the forces acting on the airplane during the takeoff or landing roll are difficult to define with simple relationships. Since the acceleration is a function of these forces, the acceleration is difficult to define in a simple fashion, and it is a principal variable affecting distance. However, some simplification can be made to study the basic relationship of acceleration, velocity, and distance. While the acceleration is not necessarily constant or uniform throughout the takeoff or landing roll, the assumption of uniformly accelerated motion will facilitate study of the principal variables affecting takeoff and landing distance. From basic physics, the relationship of velocity, acceleration, and distance for uniformly accelerated motion is defined by the following equation. S equals v squared over 2a, where S equals acceleration distance in feet, v equals final velocity in feet per second after accelerating uniformly from zero velocity, and a equals acceleration in feet per second squared. This equation could relate the takeoff distance in terms of the takeoff velocity and acceleration when the airplane is accelerated uniformly from zero velocity to the final takeoff velocity. Also, this expression could relate the landing distance in terms of the landing velocity and deceleration when the airplane is accelerated, negatively, from the landing velocity to a complete stop. It is important to note that the distance varies directly as the square of the velocity and inversely with the acceleration. As an example of this relationship, assume that during takeoff, an airplane accelerates uniformly from zero velocity to a takeoff velocity of 150 knots, 253.5 feet per second, with an acceleration of 6.434 feet per second squared, or 0.2 g, since 1 g equals 32.17 feet per second squared. The takeoff distance would be S equals v squared over 2a. S equals 253.5 squared over 2 times 6.434. S equals 5,000 feet. If the acceleration during takeoff were reduced 10%, the takeoff distance would increase 11.1%. If the takeoff velocity were increased 10%, the takeoff distance would increase 21%. These relationships point to the fact that proper accounting must be made of altitude, temperature, gross weight, wind, etc., because any item affecting acceleration or takeoff velocity will have a definite effect on takeoff distance. If an airplane were to land at a velocity of 150 knots and be decelerated uniformly to a stop with the same acceleration of 0.2 g, the landing stop distance would be 5,000 feet. However, the case is not necessarily that an aircraft may have identical takeoff and landing performance, but the principle illustrated is that distance is a function of velocity and acceleration. As before, a 10% lower acceleration increases stop distance 11.1%, and a 10% higher landing speed increases landing distance 21%. The general relationship of velocity, acceleration, and distance for uniformly accelerated motion is illustrated by figure 2.31. In this illustration, acceleration distance is shown as a function of velocity for various values of acceleration. Takeoff performance. The minimum takeoff distance is of primary interest in the operation of any aircraft because it defines the runway requirements. The minimum takeoff distance is obtained by takeoff at some minimum safe velocity which allows sufficient margin above stall and provides satisfactory control at initial rate of climb. Generally, the takeoff speed is some fixed percentage of the stall speed or minimum control speed for the airplane in the takeoff configuration. As such, the takeoff will be accomplished at some particular value of lift coefficient and angle of attack. Depending on the airplane characteristics, the takeoff speed will be anywhere from 1.05 to 1.25 times the stall speed or minimum control speed. If the takeoff speed is specified as 1.10 times the stall speed, the takeoff lift coefficient is 82.6% of capital CL max, and the angle of attack and lift coefficient for takeoff are fixed values independent of weight, altitude, wind, etc. Hence, an angle of attack indicator can be a valuable aid during takeoff. To obtain minimum takeoff distance at the specified takeoff velocity, the forces which act on the aircraft must provide the maximum acceleration during the takeoff roll. The various forces acting on the aircraft may or may not be at the control of the pilot, and various techniques may be necessary in certain airplanes to maintain takeoff acceleration at the highest value. Figure 2.32 illustrates the various forces which act on the aircraft during takeoff roll. The power plant thrust is the principal force to provide the acceleration and, for minimum takeoff distance, the output thrust should be at a maximum. Lift and drag are produced as soon as the airplane has speed, and the values of lift and drag depend on the angle of attack and dynamic pressure. Rolling friction results when there is a normal force on the wheels, and the friction force is the product of the normal force and the coefficient of rolling friction. The normal force pressing the wheels against the runway surface is the net of weight and lift, while the rolling friction coefficient is a function of the tire type and runway surface texture. The acceleration of the airplane at any instant during takeoff roll is a function of the net accelerating force and the airplane mass. From Newton's second law of motion, A equals Fn over m, or A equals G times Fn over W, where A equals acceleration in feet per second, Fn equals net accelerating force, W equals weight in pounds, G equals gravitational acceleration, G equals 32.17 feet per second squared, and m equals mass in slugs, or W divided by G. The net accelerating force on the airplane, capital F sub n, is the net of thrust, T, drag, D, and rolling friction, F. Thus, the acceleration at any instant during takeoff roll is A equals G over W times the quantity T minus D minus F. Figure 2.32 illustrates the typical variation of the various forces acting on the aircraft throughout the takeoff roll. If it is assumed that the aircraft is at essentially constant angle of attack during takeoff roll, capital CL and capital CD are constant, and the forces of lift and drag vary as the square of the speed. For the case of uniformly accelerated motion, distance along the takeoff roll is proportional also to the square of the velocity, hence velocity squared, and distance can be used almost synonymously. Thus, lift and drag will vary linearly with dynamic pressure, lowercase q, or v squared from the point of beginning takeoff roll. As the rolling friction coefficient is essentially unaffected by velocity, the rolling friction will vary as the normal force on the wheels. At zero velocity, the normal force on the wheels is equal to the airplane weight, but, at takeoff velocity, the lift is equal to the weight, and the normal force is zero. Hence, rolling friction decreases linearly with lowercase q or v square from the beginning of takeoff roll and reaches zero at the point of takeoff. The total retarding force on the aircraft is the sum of drag and rolling friction, D plus F, and, for the majority of configurations, this sum is nearly constant, or changes only slightly, during the takeoff roll. The net accelerating force is, then, the difference between the powerplant thrust and the total retarding force. Fn equals T minus D minus F. The variation of the net accelerating force throughout the takeoff roll is shown in figure 2.32. The typical propeller airplane demonstrates a net accelerating force which decreases with velocity, and the resulting acceleration is initially high, but decreases throughout the takeoff roll. the typical jet airplane demonstrates a net accelerating force which is essentially constant throughout the takeoff roll. As a result, the takeoff performance of the typical turbojet airplane will compare closely with the case for uniformly accelerated motion. The pilot technique required to achieve peak acceleration throughout takeoff roll can vary considerably between airplane configurations. In some instances, maximum acceleration will be obtained by allowing the airplane to remain in the three-point attitude throughout the roll until the airplane simply reaches lift equal to weight and flies off the ground. Other airplanes may require the three-point attitude until the takeoff speed is reached, then rotation to the takeoff angle of attack, to become airborne. Still other configurations may require partial or complete rotation to the takeoff angle of attack prior to reaching the takeoff speed. In this case, the procedure may be necessary to provide a smaller retarding force, D plus F, to achieve peak acceleration. Whenever any form of pitch rotation is necessary, the pilot must provide the proper angle of attack, since an excessive angle of attack will cause excessive drag and hinder, or possibly preclude, a successful takeoff. Also, insufficient rotation may provide added rolling resistance or require that the airplane accelerate to some excessive speed prior to becoming airborne. In this sense, an angle of attack indicator is especially useful for night or instrument takeoff conditions, as well as the ordinary day VFR takeoff conditions. Acceleration errors of the attitude gyro usually preclude accurate pitch rotation under these conditions. Factors affecting takeoff performance. In addition to the important factors of proper technique, many other variables affect the takeoff performance of an airplane. Any item which alters the takeoff velocity or acceleration during takeoff roll will affect the takeoff distance. In order to evaluate the effect of the many variables, the principal relationships of uniformly accelerated motion will be assumed, and consideration will be given to those effects due to any non-uniformity of acceleration during the process of takeoff. Generally, in the case of uniformly accelerated motion, distance varies directly with the square of the takeoff velocity and inversely as the takeoff acceleration. S sub 2 over S sub 1 equals the quantity V sub 2 over V sub 1 squared times the quantity A sub 1 over A sub 2, where S equals distance, V equals velocity, A equals acceleration. Condition 1 applies to some known takeoff distance, S sub 1, which was common to some original takeoff velocity, V sub 1, and acceleration, A sub 1. Condition 2 applies to some new takeoff distance, S sub 2, which is the result of some different value of takeoff velocity, V sub 2, or acceleration, A sub 2. With this basic relationship, the effect of the many variables on takeoff distance can be approximated. The effect of gross weight on takeoff distance is large, and proper consideration of this item must be made in predicting takeoff distance. Increased gross weight can be considered to produce a threefold effect on takeoff performance. 1. Increased takeoff velocity. 2. Greater mass to accelerate, and 3. Increased retarding force, D plus F. If the gross weight increases, a greater speed is necessary to produce the greater lift to get the airplane airborne at the takeoff lift coefficient. The relationship of takeoff speed and gross weight would be as follows. V sub 2 over V sub 1 equals the square root of W sub 2 over W sub 1. EAS or CAS. Where V sub 1 equals takeoff velocity corresponding to some original weight, W sub 1, and V sub 2 equals takeoff velocity corresponding to some different weight, W sub 2. Thus, a given airplane in the takeoff configuration at a given gross weight will have a specific takeoff speed, EAS or CAS, which is invariant with altitude, temperature, wind, etc., because a certain value of lowercase q is necessary to provide lift equal to weight at the takeoff capital CL. As an example of the effect of a change in gross weight, a 21% increase in takeoff weight will require a 10% increase in takeoff speed to support the greater weight. A change in gross weight will change the net accelerating force, Fn, and change the mass, m, which is being accelerated. If the airplane has a relatively high thrust-to-weight ratio, the change in the net accelerating force is slight, and the principal effect on acceleration is due to the change in mass. To evaluate the effect of gross weight on takeoff distance, the following relationships are used. The effect of weight on takeoff velocity is V sub 2 over V sub 1 equals the square root of W sub 2 over W sub 1. Or, the quantity V sub 2 over V sub 1 squared equals W sub 2 over W sub 1. If the change in net accelerating force is neglected, the effect of weight on acceleration is A sub 1 over A sub 2 equals W sub 2 over W sub 1. Or, A sub 2 over A sub 1 equals W sub 1 over W sub 2. The effect of these items on takeoff distance is S sub 2 over S sub 1 equals the quantity V sub 2 over V sub 1 squared times the quantity A sub 1 over A sub 2. Or, S sub 2 over S sub 1 equals the quantity W sub 2 over W sub 1 times the quantity W sub 2 over W sub 1. Or, S sub 2 over S sub 1 equals the quantity W sub 2 over W sub 1 squared. At least this effect because weight will alter the net accelerating force. This result approximates the effect of gross weight on takeoff distance for airplanes with relatively high thrust-to-weight ratios. In effect, the takeoff distance will vary at least as the square of the gross weight. For example, a 10% increase in takeoff gross weight would cause a 5% increase in takeoff velocity, at least a 9% decrease in acceleration, at least a 21% increase in takeoff distance. For the airplane with a high thrust-to-weight ratio, the increase in takeoff distance would be approximately 21 to 22%, but for the airplane with a relatively low thrust-to-weight ratio, the increase in takeoff distance would be approximately 25 to 30%. Such a powerful effect requires proper consideration of gross weight in predicting takeoff distance. The effect of wind on takeoff distance is large, and proper consideration also must be provided when predicting takeoff distance. The effect of a headwind is to allow the airplane to reach the takeoff velocity at a lower ground velocity, while the effect of a tailwind is to require the airplane to achieve a greater ground velocity to attain the takeoff velocity. The effect of the wind on acceleration is relatively small and, for the most part, can be neglected. To evaluate the effect of wind on takeoff distance, the following relationships are used. The effect of a headwind is to reduce the takeoff ground velocity by the amount of the headwind velocity, V sub W. V sub 2 equals V sub 1 minus V sub W. The effect of wind on acceleration is negligible. A sub 2 equals A sub 1. Or, A sub 1 over A sub 2 equals 1. The effect of these items on takeoff distance is S sub 2 over S sub 1 equals the quantity V sub 2 over V sub 1 squared times the quantity A sub 1 over A sub 2. Or, S sub 2 over S sub 1 equals the quantity V sub 1 minus V sub W over V sub 1 squared. Or, S sub 2 over S sub 1 equals the quantity 1 minus V sub W over V sub 1 squared. Where S sub 1 equals 0 wind takeoff distance, S sub 2 equals takeoff distance into the headwind, V sub W equals headwind velocity, and V sub 1 equals takeoff ground velocity with 0 wind, or, simply, the takeoff airspeed. As a result of this relationship, a headwind which is 10% of the takeoff airspeed will reduce the takeoff distance 19%. However, a tailwind, or negative headwind, which is 10% of the takeoff airspeed will increase the takeoff distance 21%. In the case where the headwind velocity is 50% of the takeoff speed, the takeoff distance would be approximately 25% of the zero-wind takeoff distance, a 75% reduction. The effect of wind on landing distance is identical to the effect on takeoff distance. Figure 2.33 illustrates the general effect of wind by the percent change in takeoff or landing distance as a function of the ratio of wind velocity to takeoff or landing speed. The effect of runway slope on takeoff distance is due to the component of weight along the inclined path of the airplane. A runway slope of 1% would provide a force component along the path of the airplane, which is 1% of the gross weight. Of course, an upslope would contribute a retarding force component while a downslope would contribute an accelerating force component. For the case of the upslope, the retarding force component adds to drag and rolling friction to reduce the net accelerating force. Ordinarily, a 1% runway slope can cause a 2 to 4% change in takeoff distance depending on the airplane characteristics. The airplane with the high thrust-to-weight ratio is least affected, while the airplane with the low thrust-to-weight ratio is most affected, because the slope force component causes a relatively greater change in the net accelerating force. The effect of runway slope must be considered when predicting the takeoff distance, but the effect is usually minor for the ordinary runway slopes and airplanes with moderate thrust-to-weight ratios. In fact, runway slope considerations are of great significance only when the runway slope is large, and the airplane has an intrinsically low acceleration, i.e., low thrust-to-weight ratio. In the ordinary case, the selection of the takeoff runway will favor the direction with an upslope and headwind rather than the direction with a downslope and tailwind. The effect of proper takeoff velocity is important when runway lengths and takeoff distances are critical. The takeoff speeds specified in the flight handbook are generally the minimum safe speeds at which the airplane can become airborne. Any attempt to take off below the recommended speed may mean that the aircraft may stall, be difficult to control, or have a very low initial rate of climb. In some cases, an excessive angle of attack may not allow the airplane to climb out of ground effect. On the other hand, an excessive airspeed at takeoff may improve the initial rate of climb and feel of the airplane, but will produce an undesirable increase in takeoff distance. Assuming that the acceleration is essentially unaffected, the takeoff distance varies as the square of the takeoff velocity. S sub 2 over S sub 1 equals the quantity V sub 2 over V sub 1 squared. Thus, 10% excess airspeed would increase the takeoff distance 21%. In most critical takeoff conditions, such an increase in takeoff distance would be prohibitive, and the pilot must adhere to the recommended takeoff speeds. The effect of pressure, altitude, and ambient temperature is to define primarily the density altitude and its effect on takeoff performance. While subsequent corrections are appropriate for the effect of temperature on certain items of powerplant performance, density altitude defines certain effects on takeoff performance. An increase in density altitude can produce a twofold effect on takeoff performance. 1. Increased takeoff velocity and 2. Decreased thrust and reduced net accelerating force. If a given weight and configuration of airplane is taken to altitude above standard sea level, the airplane will still require the same dynamic pressure to become airborne at the takeoff lift coefficient. Thus, the airplane at altitude will take off at the same equivalent airspeed, EAS, as at sea level, but because of the reduced density, the true airspeed, TAS, will be greater. From basic aerodynamics, the relationship between true airspeed and equivalent airspeed is as follows. TAS over EAS equals 1 over the square root of lowercase sigma, where TAS equals true airspeed, EAS equals equivalent airspeed, lowercase sigma equals altitude density ratio, and lowercase sigma equals lowercase rho over lowercase rho naught. The effect of density altitude on powerplant thrust depends much on the type of powerplant. An increase in altitude above standard sea level will bring an immediate decrease in power output for the supercharged or ground-boosted reciprocating engine or the turbojet and turboprop engines. However, an increase in altitude above standard sea level will not cause a decrease in power output for the supercharged reciprocating engine until the altitude exceeds the critical altitude. For those powerplants which experience a decay in thrust with an increase in altitude, the effect on the net accelerating force and acceleration can be approximated by assuming a direct variation with density. Actually, this assumed variation would closely approximate the effect on airplanes with high thrust-to-weight ratios. This relationship would be as follows. A sub 2 over A sub 1 equals F capital N sub 2 over F capital N sub 1 equals lowercase rho over lowercase rho naught equals lowercase sigma, where A sub 1 equals acceleration corresponding to sea level, F capital N1 equals net accelerating force corresponding to sea level, A sub 2 equals acceleration corresponding to altitude, F capital N2 equals net accelerating force corresponding to altitude, and lowercase sigma equals altitude density ratio. In order to evaluate the effect of these items on takeoff distance, the following relationships are used. If an increase in altitude does not alter acceleration, the principal effect would be due to the greater TAS. S sub 2 over S sub 1 equals the quantity V sub 2 over V sub 1 squared times the quantity A sub 1 over A sub 2. S sub 2 over S sub 1 equals 1 over lowercase sigma, where S sub 1 equals standard sea level takeoff distance, S sub 2 equals takeoff distance at altitude, and lowercase sigma equals altitude density ratio. If an increase in altitude reduces acceleration in addition to the increase in TAS, the combined effects would be approximated for the case of the airplane with high intrinsic acceleration by the following. S sub 2 over S sub 1 equals the quantity V sub 2 over V sub 1 squared times the quantity A sub 1 over A sub 2, or S sub 2 over S sub 1 equals the quantity 1 over lowercase sigma times the quantity 1 over lowercase sigma, or S sub 2 over S sub 1 equals the quantity 1 over lowercase sigma squared, where S sub 1 equals standard sea level takeoff distance, S sub 2 equals takeoff distance at altitude, and lowercase sigma equals altitude density ratio. As a result of these relationships, it should be appreciated that density altitude will affect takeoff performance in a fashion depending much on the powerplant type. Some approximate rules of thumb may be derived to illustrate the differences between the various airplane types. A 1,000-foot increase in density altitude will cause these approximate increases in takeoff distance. 3.5% for the supercharged reciprocating airplane when below critical altitude. 7% for the turbojet with high thrust-to-weight ratio. 10% for the turbojet with low thrust-to-weight ratio. These approximate relationships show the turbojet airplane to be much more sensitive to density altitude than the reciprocating powered airplane. This is an important fact which must be appreciated by pilots in transition from propeller type to jet type airplanes. Proper accounting of pressure, altitude, field elevation is a poor substitute, and temperature is mandatory for accurate prediction of takeoff roll distance. The most critical conditions of takeoff performance are the result of some combination of high gross weight, altitude, temperature, and unfavorable wind. In A11 cases, it behooves the pilot to make an accurate prediction of takeoff distance from the performance data of the flight handbook, regardless of the runway available, and to strive for a polished, professional takeoff technique. In the prediction of takeoff distance from the handbook data, the following primary considerations must be given. Reciprocating powered airplane. 1. Pressure, altitude and temperature to define the effect of density altitude on distance. 2. Gross weight, a large effect on distance. 3. Specific humidity to correct takeoff distance for the power loss associated with water vapor. 4. Wind, a large effect due to the wind or wind component along the runway. Turbine-powered airplane. 1. Pressure, altitude and temperature to define the effect of density altitude. 2. Gross weight. 3. Temperature, an additional correction for non-standard temperatures to account for the thrust loss associated with high compressor inlet air temperature. For this correction, the ambient temperature at the runway conditions is appropriate rather than the ambient temperature at some distant location. 4. Wind. In addition, corrections are necessary to account for runway slope, engine power deficiencies, etc. Landing performance. In many cases, the landing distance of an airplane will define the runway requirements for flying operations. This is particularly the case for high-speed jet airplanes at low altitudes where landing distance is the problem rather than takeoff performance. The minimum landing distance is obtained by landing at some minimum safe velocity which allows sufficient margin above stall, and provides satisfactory control and capability for wave-off. Generally, the landing speed is some fixed percentage of the stall speed or minimum control speed for the airplane in the landing configuration. As such, the landing will be accomplished at some particular value of lift coefficient and angle of attack. The exact value of capital CL and lowercase alpha for landing will depend on the airplane characteristics, but once defined, the values are independent of weight, altitude, wind, etc. Thus, an angle of attack indicator can be a valuable aid during approach and landing. To obtain minimum landing distance at the specified landing velocity, the forces which act on the airplane must provide maximum deceleration, or negative acceleration, during the landing roll. The various forces acting on the airplane during the landing roll may require various techniques to maintain landing deceleration at the peak value. Figure 2.34 illustrates the forces acting on the aircraft during landing roll. The power plant thrust should be a minimum positive value, or, if reverse thrust is available, a maximum negative value for minimum landing distance. Lift and drag are produced as long as the airplane has speed, and the values of lift and drag depend on dynamic pressure and angle of attack. Braking friction results when there is a normal force on the braking wheel surfaces, and the friction force is the product of the normal force and the coefficient of braking friction. The normal force on the braking surfaces is some part of the net of weight and lift, i.e., some other part of this net may be distributed to wheels which have no brakes. The maximum coefficient of braking friction is primarily a function of the runway surface condition, dry, wet, icy, etc., and rather independent of the type of tire for ordinary conditions, dry, hard surface runway. However, the operating coefficient of braking friction is controlled by the pilot by the use of brakes. The acceleration of the airplane during the landing roll is negative deceleration, and will be considered to be in that sense. At any instant during the landing roll, the acceleration is a function of the net retarding force and the airplane mass. From Newton's second law of motion, A equals Fr over m, or A equals G times the quantity Fr over W, where A equals acceleration in feet per second squared, negative, Fr equals net retarding force in pounds, G equals gravitational acceleration in feet per second squared, W equals weight in pounds, and m equals mass in slugs, or m equals W over G. The net retarding force on the airplane, Fr, is the net of drag, d, braking friction, F, and thrust, T. Thus, the acceleration, negative, at any instant during the landing roll is A equals G over W times the quantity d plus F minus T. Figure 2.34 illustrates the typical variation of the various forces acting on the aircraft throughout the landing roll. If it is assumed that the aircraft is at essentially constant angle of attack from the point of touchdown, capital CL and capital CD are constant, and the forces of lift and drag vary as the square of the velocity. Thus, lift and drag will decrease linearly with lowercase q or v squared from the point of touchdown. If the braking coefficient is maintained at the maximum value, this maximum value of coefficient of friction is essentially constant with speed, and the braking friction force will vary as the normal force on the braking surfaces. As the airplane nears a complete stop, the velocity and lift approach zero, and the normal force on the wheels approaches the weight of the airplane. At this point, the braking friction force is at a maximum. Immediately after touchdown, the lift is quite large, and the normal force on the wheels is small. As a result, the braking friction force is small. A common error at this point is to apply excessive brake pressure without sufficient normal force on the wheels. This may develop a skid with a locked wheel and cause the tire to blow out so suddenly that judicious use of the brakes is necessary. The coefficient of braking friction can reach peak values of 0.8, but ordinarily values near 0.5 are typical for the dry, hard surface runway. Of course, a slick, icy runway can reduce the maximum braking friction coefficient to values as low as 0.2 or 0.1. If the entire weight of the airplane were the normal force on the braking surfaces, a coefficient of braking friction of 0.5 would produce a deceleration of half a g, 16.1 feet per second squared. Most airplanes in ground effect rarely produce lift-to-drag ratios lower than 3 or 4. If the lift of the airplane were equal to the weight, and L over D equal to 4, it would produce a deceleration of 1/4 g, 8 feet per second. By this comparison, it should be apparent that friction braking offers the possibility of greater deceleration than airplane aerodynamic braking. To this end, the majority of airplanes operating from dry, hard surface runways will require particular techniques to obtain minimum landing distance. Generally, the technique involves lowering the nose wheel to the runway and retracting the flaps to increase the normal force on the braking surfaces. While the airplane drag is reduced, the greater normal force can provide greater braking friction force to compensate for the reduced drag, and the net retarding force is increased. The technique necessary for minimum landing distance can be altered to some extent in certain situations. For example, low aspect ratio airplanes with high longitudinal control power can create very high drag at the high speeds immediate to landing touchdown. If the landing gear configuration or flap or incident setting precludes a large reduction of CL, the normal force on the braking surfaces and braking friction force capability are relatively small. Thus, in the initial high-speed part of the landing roll, maximum deceleration would be obtained by creating the greatest possible aerodynamic drag. By the time the aircraft has slowed to 70 or 80% of the touchdown speed, aerodynamic drag decays, but braking action will then be effective. Some form of this technique may be necessary to achieve minimum distance for some configurations when the coefficient of braking friction is low, wet, icy runway, and the braking friction force capability is reduced relative to airplane aerodynamic drag. A distinction should be made between the techniques for minimum landing distance and an ordinary landing roll with considerable excess runway available. Minimum landing distance will be obtained from the landing speed by creating a continuous peak deceleration of the airplane. This condition usually requires extensive use of the brakes for maximum deceleration. On the other hand, an ordinary landing roll with considerable excess runway may allow extensive use of aerodynamic drag to minimize wear and tear on the tires and brakes. If aerodynamic drag is sufficient to cause deceleration of the airplane, it can be used in deference to the brakes in the early stages of the landing roll, i.e., brakes and tires suffer from continuous, hard use, but airplane aerodynamic drag is free and does not wear out with use. The use of aerodynamic drag is applicable only for deceleration to 60 to 70% of the touchdown speed. At speeds less than 60 to 70% of the touchdown speed, aerodynamic drag is so slight as to be of little use, and braking must be utilized to produce continued deceleration of the airplane. Powerplant thrust is not illustrated on Figure 2.34, for there are so many possible variations. Since the objective during the landing roll is to decelerate, the powerplant thrust should be the smallest possible positive value or largest possible negative value. In the case of the turbojet aircraft, the idle thrust of the engine is nearly constant with speed throughout the landing roll. The idle thrust is of significant magnitude on cold days because of the low compressor inlet air temperature and low density altitude. Unfortunately, such atmospheric conditions usually have the corollary of poor braking action because of ice or water on the runway. The thrust from a windmilling propeller with the engine at idle can produce large negative thrust early in the landing roll, but the negative force decreases with speed. The large negative thrust at high speed is valuable in adding to drag and braking friction to increase the net retarding force. Various devices can be utilized to provide greater deceleration of the airplane, or to minimize the wear and tear on tires and brakes. The drag parachute can provide a large retarding force at high q, and greatly increase the deceleration during the initial phase of landing roll. It should be noted that the contribution of the drag chute is important only during the high-speed portion of the landing roll. For maximum effectiveness, the drag chute must be deployed immediately after the airplane is in contact with the runway. Reverse thrust of propellers is obtained by rotating the blade angle well below the low-pitch stop and applying engine power. The action is to extract a large amount of momentum from the airstream and thereby create negative thrust. The magnitude of the reverse thrust from propellers is very large, especially in the case of the turboprop where a very large shaft power can be fed into the propeller. In the case of reverse propeller thrust, maximum effectiveness is achieved by use immediately after the airplane is in contact with the runway. The reverse thrust capability is greatest at the high speed and, obviously, any delay in producing deceleration allows runway to pass by at a rapid rate. Reverse thrust of turbojet engines will usually employ some form of vanes, buckets, or clamshells in the exhaust to turn or direct the exhaust gases forward. Whenever the exit velocity is less than the inlet velocity, or negative, a negative momentum change occurs, and negative thrust is produced. The reverse jet thrust is valuable and effective, but it should not be compared with the reverse thrust capability of a comparable propeller power plant, which has the high intrinsic thrust at low velocities. As with the propeller reverse thrust, jet reverse thrust must be applied immediately after ground contact for maximum effectiveness in reducing landing distance. Factors affecting landing performance. In addition to the important factors of proper technique, many other variables affect the landing performance of an airplane. Any item which alters the landing velocity or deceleration during landing roll will affect the landing distance. As with takeoff performance, the relationships of uniformly accelerated motion will be assumed applicable for studying the principal effects on landing distance. The case of uniformly accelerated motion defines landing distance as varying directly as the square of the landing velocity and inversely with the acceleration during landing roll. S sub 2 over S sub 1 equals the quantity V sub 2 over V sub 1 squared times the quantity A sub 1 over A sub 2, where S sub 1 equals landing distance resulting from certain values of landing velocity, V sub 1, and acceleration, A sub 1. S sub 2 equals landing distance resulting from some different values of landing velocity, V sub 2, or acceleration, A sub 2. With this relationship, the effect of the many variables on landing distance can be approximated. The effect of gross weight on landing distance is one of the principal items determining the landing distance of an airplane. One effect of an increased gross weight is that the airplane will require a greater speed to support the airplane at the landing angle of attack and lift coefficient. The relationship of landing speed and gross weight would be as follows. V sub 2 over V sub 1 equals the square root of W sub 2 over W sub 1. EAS or CAS. Where V sub 1 equals landing velocity corresponding to some original weight, W sub 1, and V sub 2 equals landing velocity corresponding to some different weight, W sub 2. Thus, a given airplane in the landing configuration at a given gross weight will have a specific landing speed, EAS or CAS, which is invariant with altitude, temperature, wind, etc., because a certain value of lowercase q is necessary to provide lift equal to weight at the landing capital CL. As an example of the effect of a change in gross weight, a 21% increase in landing weight will require a 10% increase in landing speed to support the greater weight. When minimum landing distances are considered, braking friction forces predominate during the landing roll and, for the majority of airplane configurations, braking friction is the main source of deceleration. In this case, an increase in gross weight provides a greater normal force and increased braking friction force to cope with the increased mass. Also, the higher landing speed at the same capital CL and capital CD produce an average drag which increased in the same proportion as the increased weight. Thus, increased gross weight causes like increases in the sum of drag plus braking friction, and the acceleration is essentially unaffected. To evaluate the effect of gross weight on landing distance, the following relationships are used. The effect of weight on landing velocity is V sub 2 over V sub 1 equals the square root of W sub 2 over W sub 1. Or, the quantity V sub 2 over V sub 1 squared equals W sub 2 over W sub 1. If the net retarding force increases in the same proportion as the weight, the acceleration is unaffected. The effect of these items on landing distance is S sub 2 over S sub 1 equals the quantity V sub 2 over V sub 1 squared times the quantity A sub 1 over A sub 2. Or, S sub 2 over S sub 1 equals W sub 2 over W sub 1. In effect, the minimum landing distance will vary directly as the gross weight. For example, a 10% increase in gross weight at landing would cause a 5% increase in landing velocity, and a 10% increase in landing distance. A contingency of the previous analysis is the relationship between weight and braking friction force. The maximum coefficient of braking friction is relatively independent of the usual range of normal forces and rolling speeds, e.g., a 10% increase in normal force would create a like 10% increase in braking friction force. Consider the case of two airplanes of the same type and CG position, but of different gross weights. If these two airplanes are rolling along the runway at some speed at which aerodynamic forces are negligible, the use of the maximum coefficient of braking friction will bring both airplanes to a stop in the same distance. The heavier airplane will have the greater mass to decelerate, but the greater normal force will provide a greater retarding friction force. As a result, both airplanes would have identical acceleration and identical stop distances from a given velocity. However, the heavier airplane would have a greater kinetic energy to be dissipated by the brakes, and the principal difference between the two airplanes as they reach a stop would be that the heavier airplane would have the hotter brakes. Therefore, one of the factors of braking performance is the ability of the brakes to dissipate energy without developing excessive temperatures and losing effectiveness. To appreciate the effectiveness of modern brakes, a 30,000-pound aircraft landing at 175 knots has a kinetic energy of 41 million foot-pounds at the instant of touchdown. In a minimum distance landing, the brakes must dissipate most of this kinetic energy, and each brake must absorb an input power of approximately 1200 horsepower for 25 seconds. Such requirements for brakes are extreme, but the example serves to illustrate the problems of brakes for high-performance airplanes. While a 10% increase in landing weight causes a 5% higher landing speed and a 10% greater landing distance, it also produces a 21% increase in the kinetic energy of the airplane to be dissipated during the landing roll. Hence, high landing weights may approach the energy dissipating capability of the brakes. The effect of wind on landing distance is large, and deserves proper consideration when predicting landing distance. Since the airplane will land at a particular airspeed independent of the wind, the principal effect of wind on landing distance is due to the change in the ground velocity at which the airplane touches down. The effect of wind on acceleration during the landing distance is identical to the effect on takeoff distance and is approximated by the following relationship. S2 over S1 equals the quantity 1 minus V sub W over V sub 1 squared, where S sub 1 equals 0 wind landing distance, S sub 2 equals landing distance into a headwind, V sub W equals headwind velocity, and V sub 1 equals landing ground velocity with 0 wind, or simply, the landing airspeed. As a result of this relationship, a headwind which is 10% of the landing airspeed will reduce the landing distance 19%, but a tailwind, or negative headwind, which is 10% of the landing speed, will increase the landing distance 21%. Figure 2.33 illustrates this general effect. The effect of runway slope on landing distance is due to the component of weight along the inclined path of the airplane. The relationship is identical to the case of takeoff performance, but the magnitude of the effect is not as great. While account must be made for the effect, the ordinary values of runway slope do not contribute a large effect on landing distance. For this reason, the selection of the landing runway will ordinarily favor the direction with a downslope and headwind rather than an upslope and tailwind. The effect of pressure, altitude, and ambient temperature is to define density altitude and its effect on landing performance. An increase in density altitude will increase the landing velocity, but will not alter the net retarding force. If a given weight and configuration of airplane is taken to altitude above standard sea level, the airplane will still require the same lowercase q to provide lift equal to weight at the landing capital CL. Thus, the airplane at altitude will land at the same equivalent airspeed, EAS, as at sea level, but, because of the reduced density, the true airspeed, TAS, will be greater. The relationship between true airspeed and equivalent airspeed is as follows. TAS over EAS equals 1 over the square root of lowercase sigma, where TAS equals true airspeed, EAS equals equivalent airspeed, and lowercase sigma equals altitude density ratio. Since the airplane lands at altitude with the same weight and dynamic pressure, the drag and braking friction throughout the landing roll have the same values as at sea level. As long as the condition is within the capability of the brakes, the net retarding force is unchanged, and the acceleration is the same as with the landing at sea level. To evaluate the effect of density altitude on landing distance, the following relationships are used. Since an increase in altitude does not alter acceleration, the effect would be due to the greater TAS. S sub 2 over S sub 1 equals the quantity V sub 2 over V sub 1 squared times the quantity A sub 1 over A sub 2. S sub 2 over S sub 1 equals 1 over lowercase sigma, where S sub 1 equals standard sea level landing distance, S sub 2 equals landing distance at altitude, and lowercase sigma equals altitude density ratio. From this relationship, the minimum landing distance at 5,000 feet, lowercase sigma, equals 0.8617, would be 16% greater than the minimum landing distance at sea level. The approximate increase in landing distance with altitude is approximately 3.5% for each 1,000 feet of altitude. Proper accounting of density altitude is necessary to accurately predict landing distance. The effect of proper landing velocity is important when runway lengths and landing distances are critical. The landing speeds specified in the flight handbook are generally the minimum safe speeds at which the airplane can be landed. Any attempt to land at below the specified speed may mean that the airplane may stall, be difficult to control, or develop high rates of descent. On the other hand, an excessive speed at landing may improve the controllability, especially in crosswinds, but will cause an undesirable increase in landing distance. The principal effect of excess landing speed is described by S sub 2 over S sub 1 equals the quantity V sub 2 over V sub 1 squared. Thus, a 10% excess landing speed would cause a 21% increase in landing distance. The excess speed places a greater working load on the brakes because of the additional kinetic energy to be dissipated. Also, the additional speed causes increased drag and lift in the normal ground attitude, and the increased lift will reduce the normal force on the braking surfaces. The acceleration during this range of speed immediately after touchdown may suffer, and it will be more likely that a tire can be blown from braking at this point. As a result, 10% excess landing speed will cause at least 21% greater landing distance. The most critical conditions of landing performance are the result of some combination of high gross weight, density altitude, and unfavorable wind. These conditions produce the greatest landing distance and provide critical levels of energy dissipation required of the brakes. In all cases, it is necessary to make an accurate prediction of minimum landing distance to compare with the available runway. A polished, professional landing technique is necessary because the landing phase of flight accounts for more pilot-caused aircraft accidents than any other single phase of flight. In the prediction of minimum landing distance from the handbook data, the following considerations must be given. 1. Pressure, altitude and temperature, to define the effect of density altitude. 2. Gross weight, which define the CAS or EAS for landing. 3. Wind, a large effect due to wind or wind component along the runway. 4. Runway slope, a relatively small correction for ordinary values of runway slope. Importance of handbook data. The performance section or supplement of the flight handbook contains all the operating data for the airplane. For example, all data specific to takeoff, climb, range, endurance, descent and landing are included in this section. The ordinary use of these data in flying operations is mandatory, and great knowledge and familiarity of the airplane can be gained through study of this material. A complete familiarity of an airplane's characteristics can be obtained only through extensive analysis and study of the handbook data.